Hello, hello, hello. It's Progs. I will get. Oh, wait. Actually, there's something not good. Okay, here it is. 2 seconds. Okay. Okay. So yeah, here we go. Hello people, been a while. Well, it's been like 2 days actually, so not that much. But let's go for the advent of code. And let's go with the one from the day 6, since I didn't do it on I didn't do it during the weekend, so I have to catch up on those. And yeah, on the plan, I'm gonna try to solve the day 6 and day 7. After helping the elves in the kitchen, you were taking a break and helping them reenact a movie scene. Oh, when you over enthused jumps into the garbage chute. A brief fall later, you find yourself in a garbage smasher. Unfortunately, the door's been magnetically sealed, or so many complicated words, over enthusiastically. Oh, yeah, okay, my French accent is showing up. Enthusiast, okay. As you try to find a way out, you are approached by a family of cephalopods. We're pretty sure they can get the door open, but it will take some time. While you wait, we're curious if you can help the youngest cephalopod with her math homework. What's that? Oh no! A reference. This cephalopod math doesn't look that different from normal math. The math worksheet, your puzzle input, consists of a list of problems. Oh yeah, that. Yeah, I actually checked it out quickly. Each problem has a group of numbers that need to be either added or multiplied together. However, the problems are arranged a little strangely. They seem to be presented next to each other in a very long horizontal list. For example, all of that. Each problem's numbers are arranged vertically. At the bottom of the problem is a symbol for the operation that needs to be performed. Problems are separated by a full column of only spaces. What? Oh, yeah, okay. The left/right alignment of numbers within each other can be ignored. Got it. So this worksheet contains 4 problems. All of that. Checked their work. Cephalopod students are given the grand total of adding together all of the answers to the individual problems. In this worksheet, the grand total is all of that. Of course, the actual worksheet is much wider. You need to make sure to unroll it completely so that you can read the problems clearly. Solve the problems of the math worksheet. What's the total? So this one is going to be simple. Easy peasy. Let's copy and paste. So we have day 6. Let's remove all of that just to be sure we are using the correct test inputs. Something like that. Test. Let's remove spaces at the end, just in case. Wait, why? Yeah, okay, there are some white spaces. This is okay. You know what? I'm going to keep the spaces here, actually. Then I have my okay. Then I have my puzzle input. Here we go. Okay, so there are not that many lines, just a lot of columns. That makes sense. Yeah, that makes sense. Because it has to be the... Wait, it doesn't actually. Anyway. Oh, right, this. So... Let's go here. Let's rename that day 6. Okay. Day 6. So we have the total, of course. And what we are going to do now is, let me actually think. Yeah, this is supposed to be the same. Yeah, okay, this is all the same size, so I'm haste, so that's fine. 1 2 1 2 tests. I'm just gonna check on the music. Okay, okay, YouTube. I'm haste, so that's fine. Okay, fine. Hey. Okay. 1 band and 2 bands. Woo! That was fast. Okay, here we go. So we have a line. I guess we have the total, but I guess the best would not be to save the strings, but to save the numbers. So what I can do is directly make an array of numbers. Int array, or like table equals a list. A list. I guess I can make a list of lists technically. Let me think. I mean, I guess we have the lines. Then we want to split them. So wait, can we actually optimize this? Because, oh. Because basically the plus is commutative, right? So it actually doesn't matter if we, like the order of the addition, right? And at the end we have to add everything together anyways. So that means it actually doesn't matter as long as the end is the plus. Then you have the times, right? That is a bit more tricky. I mean, okay, let's say we have the lines. Yeah, let's not think too much about all of that. This is simple. Let's stay simple. So we have I mean, let's, yeah, okay, yeah, I'm thinking way too much. Let's get the last line, which is the operations. Operation line. This is a string. Then we are going to split all of that. We split, not the lines, just with a character that is space. Is it? Like, can I split white spaces? Because there's definitely going to be something wrong with the test input. You know, there are like some additional spaces, right? I mean, I could actually remove them, but anyway. Yeah, there's something called trim or trim. I don't remember actually. Python trim. Well, split white space. Because I'm sure that there is something. Split, that's it. Okay, that's great. So yeah, okay, that's fine. So yeah, just split without any argument, and that's good, apparently. When set to none, we'll split on any white space. So that's great. Operations. So it's a list. Well, it's a list, right? So now I'm just going to loop through every operation in operations. And if this, well, I guess I can even match operation with, well, if it's plus, I do something. Just case is enough, right? No break here, I think. Yeah, okay. Then if we have a multiplication, this is it. Actually, is a multiplication, yeah. So then we want to do things, right? Let me think a little. I mean, we could add into the array only when necessary, actually. Because we don't have the array yet, right? So operation. I mean, let's just loop through the lines. But -1 to not have the operation line. And then for every line, for every line, we're going to split. So there's going to be number that is an int, I believe. And for every number, I guess we are just going to put that in an array. Are we? For every line. I guess it's not, never mind. That's a string, right? So we have the line. Then we have line.split. This is an array of numbers. This is a string. This is an array of strings. Oh, this is complicated. This is kind of breaking my mind. An array of strings. And you want to convert each one. So I mean, yeah. Yeah, let's stay in the loop for now. Actually. How? Int. It is. Something like that. And then for numbers string, well, number strings, something like that. We loop through every number string and we add it to the list. and we just convert to an int, maybe, to int. I mean, I guess that's fine, right? I hope. The list, and we just convert to an int. Remove the volume. So we append. And I actually don't want to make a double list because it's a bit ugly, right? So instead what we can do is have the amount of columns that we have already with the split. So this is fine. Let me just think. I mean, I guess this is fine. For I in range. That. Duration equals operations I. Yeah. Just, you know, to have the same, to be uniform. And then I'm just gonna yeah, so we have the NB elements per line equal this length. So yeah, this is actually fine. And then what I'm going to do is just add all of that. So it's going to be great. Or like add let me think. Okay. So for wait. I guess I want to know this basically. Like NB. This is basically NB columns, right? And this is NB lines. NB number lines. Hey, how are you, Buttercup? Welcome. How are you doing? So for every column, we get those numbers and we add them. So this is I mean, I don't even, well, I can just total plus plus, right? Plus equal. And this is int lists. I times, I mean, I can turn that into an offset basically, which is kind of great, neat. So this is NB columns. So we start at 0 and then we boop. So this is great. And then we just add, okay, we have actually too much. This is J, let's say. So we have A and J. Number. Yeah. Then we have plus I, that is the column. So this should be it. And for the times, this is just going to be something very similar. Let's rename it into product results. And then we should have all of that. And this should be good. Let's just change the input, maybe. So yeah, just basically for those who don't know, I'm just doing the advent of code, which is like some kind of coding challenge. And here we go. Right. Okay. So now the real problems begins. Oh. Index out of range. Hey. That doesn't surprise me. So J and V colons. I mean, yeah, makes sense. 1 times 4 plus I. I is what? 0. So this is basically supposed to be... Oh, wait, int list. Oh, wait, yeah, I mean... Yeah, of course, I had to put it outside. I first put it inside because I was wondering if I was going to add this list to another list, like a list of lists, but no, that's fine. What? Oh, yeah, makes sense. Okay, let's try again. And we have a results. And is it the correct results? This is not. This is not. So what's the problem? Let's check again. Okay, first let's check if we have the correct table of numbers. So if I check debug console in here, 1, 2, 3, 3 to 8, 5, 1, 6, 4, okay. 4, 5, 6, 4, 3, 8, 7, 23, 6, 98. Yeah, this is good. This is basically what I want. So this is great. And now, it feels like this could be optimized, but maybe, never mind. Actually, we should be able to... Oh, wait. We should actually be able to know the size of the array ahead of time. So there is definitely a way to optimize this. There is definitely a way to optimize this, and we can make it even... Okay, this is actually great. So yeah, all of that we can put it at the beginning. This is a list that is going to get multiplied by the amount of line. Something like that. So that is basically this times NB colons. Okay, great. Then we have all of this, but instead of, well, we get the line, we split, but instead of appending, what do? We do I times something. Let me think. For each number. So this one is actually J. And this one is going to be I, for I in range. I mean, actually, we already know what this is, right? So then we have this. I guess this. Instead of appending, we do a equal. have this, so we do. So now I want to invert, basically. I want to invert it so that we can do the operation in the correct order, so that it could be like more optimized. Because you can potentially, how do you call that? I want to put it back into the correct order because you can vectorize, potentially, like in C++. And in Python, I'm not sure actually, but maybe Python is going to be, good enough with it. I don't know. But yeah, we can unroll loops and SIMD, all of that, if necessary. So for each column, we get, but instead I want to do I times NB numbers plus J, I suppose. Right. Yeah. Wait. I think this is it. I think this is what I want to do. Okay. And then I have yeah, so I guess, I mean, yeah, this is right. I'm getting the operation string. And then what I'm going to do is instead there, because right now we jump a lot, which is not really good. So we are going to do this instead. Right? Yeah, probably. Should be fine. Let's try. Yeah, so this is the same result, so that's good. No, never mind, this is not the same result. Index out of range. Oh. This is not the amount of column, isn't it? It's probably the amount of number lines. So let's say this is 3, that means 0, 1, 2, 3. Wait. Yeah, let's say this is 1. So 1 times. Wait. So this is this thing. So it becomes on the first row. So this is 1 times the amount of columns, yeah. Plus J. Yeah, this is correct. Is it? Oh, thanks for the follow. Hello, welcome, Black Eye. How are you? How are you doing? 3 times 4 is probably a bit of a problem. 9, 10, 11, 12. Okay, I can count. That's good. Four times 3, so this is 12. Yeah, if you do, you know about the advent of code? So let me check. This is 3. This is 4. Ha! Wait. I for each column. 0, 1, 2, 3. So 3 is fine. And now, I mean, yeah, 3 is fine. The amount of column is wrong. So I guess this is number lines. Yeah, this is number lines. Yeah, my bad. Yeah, it makes sense. Makes sense. I have this. I have the loop too. Right. So wait. Should it really? Yeah. Okay. And I guess I can pre-compute that if necessary. Fine. Thanks. Bank holiday in my country. Oh, so time for AOC pain. Yeah, I'm doing it in F sharp and Go. Never use that. Okay, so I have the same result as before, but this is the wrong result. Oh, because this is a test. Wait, even the test is not supposed to be that. So, what's the deal? Okay, let's display the total of this one. Then I mean, I guess I can do this just for like debugging purposes. And yeah, basically I've missed a few days myself of the Ludum Dare. So I'm trying to catch up, as you can see. I'm trying to do day 6 and day 7. And yeah, let's see how it goes. Okay, so times. Did I forget the... Yeah, okay, this is fine. I just have to multiply. Okay, if that's the only problem, then, I mean, everything's good, right? 4277 556, right? Yeah, this is it. So this is great. So this is working. And now I can just change the input. And we solved that problem in 30 minutes. A long time, but yeah. Day 6 was tricky how to parse. Yeah, it can be. I ended up with a list of numbers, and that's it. Here we go. Hey, right answer. First time. So now the second star. Let's see how it goes. Yeah, I'm trying to optimize a little sometimes. For example, for this one, I swapped the numbers. I have only one list. And that way, since I only have one list and that I swapped the numbers, as you can see there, then that means I can potentially here, I can potentially optimize with SIMD or like with cache and all of that. I guess it's more for like C things, right? C++, but yeah. I think in Python it does have a small impact too. Because, for example, I can pre-compute that now. I'm not doing everything right. I'm not doing micro optimizations, but I think it's important to like switch. Yeah. Second part. The big cephalopods come back to check on how things are going. When they see that your grand total doesn't match the one expected by the worksheet, oh no, they realize they forgot to explain how to read cephalopod. No! Cephalopod math is written right to left in what? In columns, okay. Each number is given in its own column. With the most significant digit at the top and the least significant digit at the bottom. right to left in columns. What? I'm gonna try to understand what they're saying. Problems are still separated with a column consisting of only spaces, and the symbol at the bottom of the program is still the operator to use. So here's a problem. So let's see. Regarding the problems right to left, one column at a time, the problems are not quite. How now? Okay, they are now quite different. Okay, the one on the right is 4 plus 4, 3, 1. Wait, what? 4, 3, 1. What? Rightmost problem. So this is this one, right? This is a plus. Yeah, this is it. So 4. Is it up on the least significant digit at the bottom? 4. Why not 46 plus 431 431 plus 623? What the hell? Six was tricky. Yeah, okay, I understand now. Wait, what? You don't even understand how it's... The rate must... Wait, second problem from the right is 175. Okay, this is good. 581, 32. Okay, I can understand that. I can understand that. Third is, let me see, 8 plus 248 plus 369. 8, 248, 3. Okay, this is good. So yeah, actually they're not aligned. These ones are aligned, but not these ones. So this one is 434. Wait, no, this is actually 4. Oh, 4 plus 3, 4, 3, 1. Okay, I understand now. I understand. Yeah, I shouldn't have optimized it like that. I shouldn't have optimized it. Okay, this time we can actually use something a bit better because it's like from right to left and it's starting with the 4, right? But what we can do is the opposite because where is it? Yeah, 623 plus 431 plus 4 is the same as 4 plus 431 plus 63, right? So this is fine. This is fine. I mean, yeah, okay, let's... This one is not fun. This one is not fun. Boom. So, how are we going to do that? For now, we just have numbers. I mean, I guess we can keep them actually. I mean, yeah, we can actually just keep them. Because now we just have to change what's here, right? Yeah. Yeah, that doesn't change anything, does it? Oh yeah, that makes it actually more complicated. Because now I have to split myself with the percent, with the modulo. I have to do extra modulos. Oh no. I'm just going to put strings actually. So now I don't cast. I have this. This is a string. So this is a star list maybe. Like int str list, let's say. Okay. And now let's check back what we have to do. I guess we have to split. So wait, 4, 3, 1. Let me check. So this is 4 plus 4, 3, 1. Okay, let's do the opposite. We can start by the left because this is right. We can just add because it's an addition at the end, so we can just start by the beginning. Yeah, so this is 1 times this. Wait, 1? That's most problem. Wait. Oh no. Wait, what? Why is this one not aligned the same as for the others? Wait, wait, what? Wait, this one is weird. Like for this one, the 4 is like alone. But for this one, there should be alone. There should be on the left, right? Wait. Oh, do space matter? Maybe space matter. Each number is given in its own column. Oh. Okay, so spaces do matter this time. Spaces do matter. Okay, so this is actually even easier than what I thought, because now I can... let me check again, just in case. But I can basically... Okay, I still need the split for the operations, but for those I can just put a space. And now every string should be the same. Like the same amount of characters. So what I should do is... Wait, actually, let me let me think, because so I start. Since I inverted things, it should be... What should it be? I guess the first character plus the first plus the first. As integers. So for every line, Yeah, this is tricky. For every line, for every character. So for every line, for every character, let's call it. How should we call it? I guess I actually have to do the opposite. Let's maybe just remove that for now. For every line. So wait. For every column and then for every line. So I'm starting with these. And I'm just, well, for every column and then for every line. Okay, let's say we have that. Or do we? Yeah. For every line, for every character. So let's just get the number. The number is going to be this in string. So then we have the first one. Well, NV characters equals length. For every character in this, then we are going to get this. Okay. And yeah, that should be the opposite. I want to invert the loops, but I can't really just do that because then I don't have my characters anymore. I guess I can just take the 0. For every character. Yeah, let's invert that. So we have something like that. We have this, and enemy character is just is it like always the same? 4, 3. Okay, this is not. Yeah, this is definitely a bit tricky. But you know what? We can just have something like numbers. This is so bad. Final numbers. Well, final components, let's say. Components? Final numbers. ST. Well, actually, yeah, STR. And this is a list of strings. And then for every character we append this thing. And okay. Wait, we don't append. Wait, we need. Wait. Okay. So this is K. Okay. Plus equal this. And K. Yeah. I have to insert. Because I have to make it long enough for K to be good, right? So yeah, definitely a bit tricky. I guess. Yeah, let's not do that. Let's not do that. I guess the goal is to have a single string that for every line, everything in the line, we get each character. Okay. Okay. So we have for each character, we're going to do that a bit later, but for each character, for everything, for every element in the line, we have nb equals nb strings, nb string, this is it. Then we just plus equal this. And then since this is a string, we can just get K. Yeah. At the end, we can just convert that into an int. And we just do the thing, right? So this is like total equals 1. Total times equal this. And then we total plus equal product result, right? Should be it, right? And I don't need a split. Yeah, I don't need a split, right? Yeah, yeah, because a string is just a string. So now what I can do is, I don't know this, so I'm going to set it to the length of the first one, so J. Well, I ignore J because J is inside the loop, so I don't know it yet, and it doesn't matter. And I feel like that's it. Well, actually I have to take the length. And yeah, that should be it. Should be a lot better. If I remove this, now I should just be able to do the same there. Just copy and paste. Yeah, yeah, let's skip this though. Wait, total. Oh no, that's product results. Here we go. Then I can copy that. Boom. So this starts at 0. Then we do all of this. Oh wait, yeah, okay, and then we add. And this is good. That should be good. Is that it? I'm actually not sure. 42770. Nope. So this one, right? Let's maybe just breakpoint and check. Okay. Is it even running? What? Oh! My bad. So I still have a chance actually. This might not be the end. This is just the wrong day. Well, the wrong part. Okay, I don't have a chance. Content. Out of range. K. What's K? 0. What? You're telling me this is too much? Number line should be fine. String index out of range. String, not array. String. So what's this? Wait, what do I have? Strings. Why do I have strings that are not set? This is kind of bad. Number line. Is it because of that? Oh no. Number string. That makes sense. But what? Doesn't actually. So is it supposed to be a space? Is it because I removed the spaces? Okay. Actually, that might be because of it. This one didn't have one, right? But it should be at the end. Well, it was at the end, so that should be fine. Let's try again. One, two, three. Yeah, let's compare. So 1, 2, 3. Nah. Oh, 4, 5, 6. 3, 2, 8. 4, 5 is like. What? Isn't it supposed to be 4, 5? Like right there. I mean, I guess number strings is wrong. What about line? Line is right. Oh. Oh yeah. I have to do the split manually, right? Yeah, you were right. Tricky to parse. So basically I have to ignore the first spaces. And until I find a number. And then that counts in. So basically, while I find something that is not a space, wait. I mean, yeah, there can be zeros on the right too. Oh no. There can be zeros on, well, empty spaces on either side, which is kinda bad. Yeah, it was painful to process. I was reading column-wise. Yeah, I see. Um, yeah, I mean, you're not wrong. Like, I guess just, yeah, I mean, just reading the lines would be actually better. Oh, what was that? Oh, new music. Yeah, I understand what you did, and maybe you should do that too. Like, it's actually better, right? Like 1000, yeah. Let's remove everything. Because, yeah, I don't actually have to split. The reason why we had to split in the first place was because of the empty spaces and stuff, right? But actually, after splitting the lines, we don't need that. Basically splits the operations, which is good. So then we can still get this. Okay. So this is fine, the match is fine. Well, actually, the split is... Huh. Because I guess the good thing is that the operation is always on the first character, right? Like, wherever I look at, it's like the first, right? So I guess that can give us some idea. It's always on the first. Good. So that means I could what? Instead, let's do that. Operation line, split. Yeah, let's reset everything. And reading from the right to left was even easier. Was it? I don't necessarily see why, but... Oh, because you... yeah, I can see why. Because you have the stop, right? The operation is the stop. But I mean... I mean, that's fine. I'll do left to right. So for every... Well, let's actually just loop. We have the total equals 0, while... while what? Yeah, I'm going to remove this line. Let's actually just do a... For I in range A. For every character in here, operation line, then if actually, I guess it's a match. Is it? Yes, exactly. So if you read from right to left, you know when a block finishes. Yeah, yeah. Makes sense. Yeah, I guess the problem also says that it's from right to left, right? Um, oh no, but then how do you know the? Well, I guess you do know the operation, right? But uh, ah, yeah. Let me think. I realize because that's exactly how they do it in the sample data. Yeah, yeah, that's what I'm thinking too. But uh, anyway, yeah, fine. Let's do it. -1, -1. So this is going from, it's reversed. Um, Now I'm going to have, um, actually, I equals 0 while I is higher or equal to 0. Then I do stuff. No, no, yeah. Um, then I have, while this is a space, this is actually not 0, this is the length of this line, -1. And while this is a space, then I minus minus. After that, I have a character that I can match. Uh, well, let's have a start equal I. I have an end equals I. I have the match. So basically, I'm trying not to make a list. Um, so I match the current character. If this is a plus, then something. Um, Pass. Yeah, I guess that's it. If this is, I guess I need a case. If this is a times, then something. And now I'm just going to do I guess actually I can start by the end from left to right. So for J in range, like for C in range, uh, so from end to start +1 because we include it. Wait, no, that's not going to be good anymore. That's not going to be good. I should not look through the characters. This is for each column. Well, I guess this is inside, so... Wait. Yeah, this is fine. And for every character, I do something, and then I do for each column, for each line. My bad. So I. So this is J for J in range. Variation. My chat is always moving. I don't know why. It's just so bad. Like no one is writing a message right now, but I see it moving, so I always like look. But there's just basically I think Twitch running an ad. I'm so sorry about that. So J J J J J. So we have this. This is character. So now this is from 0 to len of lines -1. Oh, thanks for the raid. Hello, Daniel. How are you? Thanks for the raid. Let's shout out. Daniel TM. Hey. How are you doing? How was the stream? So for all of those, I have a string that is first empty. Then I'm going to add for everything, well, for every line, I add the character on that line. So this is lines J, I. Oh, okay. And yeah, this is actually it. And then now that I have the string, I can actually convert it into an int. And now I can actually compute even the total. So expression total equals 0, like there. Hey, good, made a new spaceship design for my game. Oh, simpler design, but also drew the normal map by hand. Oh, like the normal map is like it's always like so great. Well done. I mean that's a good technique. Yeah, in 2D does like make some stuff right. Because I guess you can like generate it with like kind of algorithms like AI, like machine learning, with whatever, right? But I guess by hand is like always the best too. So that's great. Well done. I do want some normal maps for my own game, but not. I guess it's still a work in progress, so maybe not right now. That's a priority. So yeah, we have a plus here, and we have here. Wait, so we have a string, and we plus. Okay, that's good. Actually, this is not because for the times it is 1, right? It's not 0. So let's do that. I guess I could make a function get number or something, right? But this is fine. This is times. This is this is 1. And that should be good. Actually, I have to total plus equal expression total. I've tried generating, but it's always bad. Yeah. Hand-drawn normal and specular maps are great. You get reflections and shine exactly where you intend them to appear. Oh, you did the specular too? Yeah. Glass reflects mud and metal, etc. Yeah, yeah, yeah. I mean, yeah, it looks nice. Yeah, to be honest, I wasn't even thinking about the specular. I mean, I know what it is, but I basically thought about my game, about normals for my game. But I guess in general, I haven't really paid a lot of attention about like specular maps in 2D. But that's actually a nice idea. I guess. Yeah, never mind. Yeah, specular can be a good idea. I was thinking that, you might not want specular on everything, right? Like if you have a character, then maybe it's a bit different. Maybe actually I wonder like how it would be like for the eyes. If you have like some specular, uh, would make it look like maybe a bit alive, right? Because then you would have like the light reflecting in the eyes, kind of. To be seen. Um, what's that? Invalid literal for what? Is it? Oh, it's plus equal. My bad. Yeah, of course it's not going to do anything. Yeah, so jewelry. Yeah, yeah. I mean, specular for me is like metals, right? But like, I guess it's more realistic metals for me. So that's why I wasn't really thinking about it in a 2D game, right? Because usually 2D games are, um, they're like either, well, not metal, I guess. And when there is metal, then it's not usually realistic, right? So yeah, I think we don't really see that much because of that. But that's a good. Yeah, I would have to try that out. Why is it so slow? Oh no, I know why. Oh, so I have to do the -1 somewhere. Like yeah, minus minus minus. Okay, 105. This doesn't seem to be it. Huh? But this is a lot. What? Oh, NB string. Let's say. Okay, now let's try to see how this is. I suppose. So we have. We start at 14, so basically there, right? We continue, a space, to space, we got it. So we have the start and the end. Start should be 14, end should be 12. Yeah. I mean, I guess I should maybe swap the name of the variables, but that's fine. So we have a plus, yep. Expression is 0. We start. Wait, I'm not using C. Oh no. Oh no, that's why. That's why. What is C? So this is actually this one, right? Yeah, I think this is it. Yep. Let's try again. Oh no. Int. What? Invalid literal. Ah. Can I try again? Ah. Okay. So this is nothing. J. Yeah. Yeah. So this is lines. This is lines J. Let me. Yeah, I'm going to. Whoop. Line J is the first line. This is good. And now C is 12. So if I do that, 12. 6. Why? Oh yeah, because I start with. Yeah, okay, this is fine. 6 to 3. Right? So do. Then this is 6 to 3, which is good. It's the one at the end. So 6 to 3 plus 4 3 1, right? 4 3 1. We add it probably somewhere. Yep. Sounds good. And then we have nothing 4. Oh, that's right. Nothing 4. Here we go. So this is good, right? I mean, that looks good to me. And this should be 1058. This is correct. Perfect. -1. We continue. We find a plus. A multiplication. 1. Oh, did I forget something here? So we have nothing. Then we have nothing. 3, 2. Yep. Then I multiply this, and I get a 2. A 32. I continue. 5, 8, 1. 5, 8, 1. I multiply. This is good. This is good. This is perfect. And then I have 175. 175. And this is correct. Wait, why is it continuing? Oh no. Wait. Oh. -1. Minus. Oh. So this is -2. Oh. This is it. Okay, I get it now. And let's remove that. Okay, 3, 2, and now this is the correct number. And this is going to be good. Share the difference of with and without normal and specular maps. As I'm getting shot at, the light reflects from the player's ship. Can I share on the stream? Cool, yay. Poor C. Nobody likes it. Yeah. Yeah. Wait. Sure. Yeah, let me download. Do. And then we have. So basically, this is a spaceship. Let me do it small. This is spaceship. And this. Oh wait. This is a spaceship too, right? 2 seconds. And let's zoom. So yeah, this one is like just the texture directly, right? Without the speculars and the normal and everything. And this one is with. And yeah, I think I mean, we can see that. I mean, I guess there's like less, you could say less lights too compared to here. And yeah, well, we can definitely see that this is supposed to be the same color as here, right? This is gray, but when you look there, you can see that this is totally different with like the light and the specular. Like this is totally white uh, because of the shot, and then we have, you know, something less white here, more gray. And I guess that without the shoot, then it's like coming back to this color around that. So I mean, yeah, looks nice. Sure. And yeah, this is the actual number, right? Yeah, that should be it. So let's submit. Here it is. And completed. Okay, so this one was in 1 hour and 30 minutes. Okay, I have to do the next one because I have to catch back to the advent, right? But it's going to be a bit tricky for the 8. So I'm probably going, you know, to just do the 7 and that's it. GG, thanks. So you thank the yeah, I thank you. You thank the cephalopods for the help and exit the trash compactor, finding yourself in the familiar halls of a North Pole research wing. Based on the large sign that says Teleport Hub, they seem to be researching teleportation, or you can't help but try it for yourself and step onto the large yellow teleporter pad. Suddenly, you find yourself in an unfamiliar room. The room has no doors. The only way out is the teleporter. Unfortunately, the teleporter seems to be leaking magic smoke. Oh no. There's really a Wikipedia for that. Oh, okay. Okay. I mean, yeah. Okay. Since this is a teleporter lab, there are lots of spare parts, manuals, and diagnostic equipment lying around. After connecting one of the diagnostic one of the diagnostic tools, it had. I'm a programmer. I should be able to say that. Okay, diagnostic, yeah, diagnostic, diagnostic. Oh, diagnostic actually sounds good. Diagnostic tools. It helpfully displays error code. Oh no! Which apparently means that there's an issue with one of the tachyon manifolds. A tachyon is supposed to be faster than light, right? That's the particle that's supposed to be faster than light. Hypothetical particle. Yeah, yeah. I'm so good at physics. That's the only particle I know. You quickly locate a diagram of the tachyon manifold. Okay. You press an input. A tachyon beam enters the manifold at the location marked S. Wait, what? Okay. Tachyon beams always move downward. Okay. What? Tachyon beams pass freely through empty space. However, if a tachyon beam encounters a splitter, the beam is stopped. Instead, a new tachyon beam continues from the immediate left and from the immediate right of the splitter. So it goes there, then all of that. Okay. In this example, the incoming tachyon beam extends downwards from S until it reaches the first splitter, and then it continues. Okay, I get it. What's the point? 3 Taken beams. Okay. To repair the teleporter, you first need to understand the beam splitting properties of the Taken manifold. Okay, in this example, the Taken beam is split a total of 21 times. Oh, so I have to count 1, 2. Oh, wait, no, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh wait, I actually don't have anything here. I mean, okay, that's fine. There are also stars which light up the ships and planets. Oh, yeah, the spaceship was actually rotated in a way that the light occluder didn't let the lights to shine on the ship. The light occluder is on the tail, and because the tail is like a cone, it overrides the nearby stars affect the light. I mean, yeah, I think in video games, actually, if you want to make a big difference between, a game that looks cheap and a game that looks good, I think the lighting is like one of these things. Lighting and particles, like very important. So yeah, hopefully it goes well, because I guess you're still, working on stuff, right? Like, I don't know if you're planning to do that for the enemies. I don't remember the enemies. Oh yeah, I guess you already did that actually. Oh wait, actually it doesn't seem. I don't know. Because the light is the same, right? Like behind, so maybe not. But yeah, good luck. But overrides the nearby stars. Yeah. Okay, so we have all of this. I mean, it seems quite simple. How many times? Let's do this. Maybe we can do the last one. Maybe not. Probably not. Boom. Let's remove. So we have this. Yeah, I guess we still want to split the lines. This is day 7. Day 7, right? Day 7 input. Okay, let's get started then. I guess I'm just going to copy quickly the thing, not this one. This one. Let's input. Yeah, then we have the input. Boom. Ooh, so big. Okay. Here we go. So test input first. I mean, actually, we could well, actually, no, because we're going to debug, so I don't want to display both. But yeah, let's start with that. So I have to. Okay, strategy. We are going to look at the first line because, okay, it's on the first line, right? I mean, we have the example anyways, right? The puzzle input, and on the puzzle input, that's all we're going to use. It's on the first line. So let's consider that this is on the first line. So we are going to find the S, and this is the I, basically. We're going to find a I. So I equals 0, while lines I is not S, then we need plus plus, right? Hello, Tunnel Raid! Welcome! Locking still at work, but hi, hello! Enjoy your work. So yeah, we find the S. So now that we have that, this is J equals 0. So I guess I'm going to do while Uh, hmm. Hmm. Yeah, j equals actually it's going to be 1 because we already know that there is a s on the first one. So while this is dot, maybe? No, not while this is less than the length of the lines, like the amount of lines. So NB lines equal this, just to remember better, right? While this is less, then we plus plus. And before that, we're going to, oh wait, this is actually, I mean, we could have a recursive function for this, but I don't want to, so maybe we can have a list of beams. Um, a list of beams. So what do I have to count actually? It's split like 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yeah, 21. Okay. So probably 21. Wait, actually, I'm not so sure now because there was a space too. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Wait, there are 22 things. I don't understand. Proxy gave me the first raid ever. Oh. I'm glad I had this opportunity. This is now on my U record and on yours forever. Wait, I'm actually just trying to compute this because I don't think I understand. So 1, 2, 3, 4, 5, 6. Or maybe it's at, oh, maybe it's the end. No, never mind. There's not enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So yeah, actually, wait, I actually don't understand. I actually don't understand. Oh, because it's 22, but minus 1 because it's a split, right? Yeah, that's probably because of that. I don't know. I don't know. Yeah, you have a really hard time right now at counting stuff. But I guess we can just try it, right? And then if it doesn't work, then we're going to do a minus 1, a plus 1, minus 1. And it's going to work, and everything's going to be fine. So a list of I guess you only want to count each one only once, right? This is the thing. You want to be careful about that. So until it reaches. I guess J. I mean, J is fine. It's the I that's a problem. So okay, this is fine. So we have if this is a dot. So if lines J, I guess for now it's going to be I, but it's going to change, right? If this is a dot, then we just go deeper. Brr, brr, brr. Taken beams in taken beams are hard. Oh, over. I thought they were like very small, so you should be able to, you know. Anyways, yeah, I mean, I could just do a recursive, but since it's this big, I guess actually it's not that big. Yeah, I mean, recursive wouldn't even really work. I mean, you could like have some cache, I suppose, though, that would work. But yeah, the best way is iterative. So minus. Actually, it's plus. Wait, and it's I. Wait, what? What am I doing? No, it's not I. It's J. Okay, what am I doing? So I have that. Okay. So now I have Elif. If this is this, the boop, right? Yeah. Just ensuring that this is the same character. Yeah. If this is it, then I'm going to split it. Just wait. Yeah. How do I split it? I was thinking about making a list. I guess it's actually a set. Or like a map. Oh. I actually have an idea. Maybe not. I mean, I guess I could just do line by line, but I don't really want to. Because yeah, basically you could just process it like as if it was a 2D array, and you can just go line by line, and you can just use like some kind of rule, like if the neighbor is S on top, then on the current cell you have the thing, and yeah, you can basically just do what they did, uh, which would be like really simple. I mean, yeah. But to destroy my computer. Oh no. Yeah, I'm starting to have an idea actually. Like we are going to have BAM, no, beams equals an array. So this is a list of int. Then inside we are just going to put um, just append, not with an index. We are going to put I, okay, and J we're just going to go down, okay. If this is yeah, beams. Let's pop. So this is current I. Wait. Yeah, I beam, let's say. Boom. Boom. So we pop. Then here we add, well, we plus equal 1. At the end, actually, not now. Let me think. actually for every beam, well, I beam in beams, for everything there, I do something. Well, I mean, I'm going to clear it. I want to clear this thing. So yeah, this is actually, let's have next beams, something like that. At the beginning, we have this. I guess I can actually put the eye directly there. I have the beams equal next beams. I have next beams dot clear. I have beams. So this is at the end. We increase at the end only. And for each beam, I'm going to append. So if this is a dot, this is basically the one that is going to be on the same column. So this is just this. And if we split, then we are going to have that plus 1 and that minus 1, okay? But then there's going to be a problem, as you can figure out, is that we want a set because we are going to have the same rays. Well, we are going to have rays on the same at the same place, right? Proxy, I leave a lurk and go scavenge for food. Okay, enjoy. And yeah, basically the problem there is that we actually want to ensure that this is not like multiplying forever. So what I want is verify that this is unique, that each column is unique in each beam, like each number is unique in the beam, right, in beams. But to do that, I have to use, I have I have three, okay, I have four possibilities. The first one is every time I want to check, every time I check, and this is ON, right? Because I check like the whole thing, I do a dot find or something like that, and this is ON, and this is really bad. Because at the time it's going to be like a lot more. Another way is to use a tree, and in this case it will be O log n. Because a binary tree, we just search, we split, we split every time in two. And this is O log n. Another way is actually O log n too, but this time with a beams array that is sorted. And we do some dichotomy, some binary search. So like, is it more than 50? If yes, then we search between 50 and 100, right? This kind of stuff. Another way, if we want to have it be even less, that is amortized O1, we can have a hash map. And this is amortized because we can have some collisions. But this is O1. And then even better, we can have O1, but true O1, with just basically a lookup table. And I think this is what I'm going to do, because this way we are going to sacrifice, well, I'm going to tribute some memory, let's say, for the good of all, for the performance. So I have beams, I have next beams. Yeah. Yeah. Yeah, so this is line. This is a list of integers. Let me actually check what I have. Test input. So yeah, okay, input is actually really big. So we want O1 for this. We want O1. We want some performance. And this is going to be 0 times So the size of the array is just something like lines 0, and this is the length of that line, of the first line, because it's a square, right? As you can see. So this is fine. So we have a line. Well, let's call it lookup table. So this is not a, well, I mean, I guess this is actually Booleans. And we are only going to check if this is, well, if there is array or not. AOC, hello Fog, how are you? Fog the Catman. Doing the day 7. 7? Yeah, 7. With a lookup table. Good, you? I'm good, thanks. And yeah, did you do the Advent of Code 2? What day are you at? Or at the last one, maybe? The latest one? Day 8. So anyway, I have all of that. Now the difference is for the one that is at I. So I, here, is going to be true because there is actually a beam. Yep, I just got all caught up this morning. Oh, yeah, I still have to do that myself. For now, it's just the first part of day 7, so you may have already done it. But, you know, I'm going to try to optimize. I don't know if you optimized or not. And then, you know, there is part 2 that we are going to see. I don't know what it is at all, but yeah. Yeah, at first I wasn't sure how to go at it, but actually it looks quite simple now that I have the ID. So I have the lookup table. If this is a dot, then this is the same because it goes on the same line. But if there is a split, then what am I going to do? I'm going to verify if for the lookup table I beam. I guess I have to be careful about not overflowing. But let's say we don't care for now. Mine ended up running fast enough, so I didn't optimize much. Let me get times for you. Okay. So yeah, if this is false, so not. If this is false, then we are going to append it because it's a do once, and then we set that to true, so we don't do it again, right? So we don't add it again. And same logic, just right here. I do the +1. If +1 is already true, I don't do it. If this is not, then I set it to true. And I feel like I should actually put that into a variable, but I right beam maybe? Wait, yeah. I left beam. I left my beam. I left my beam behind. So left. We have the right. Whoop. And whoop. So here we go. And that way we only add it one time. We have the O1 comparison. We don't make a list every time. We only change what changes. And actually I forgot something, but the line where we split, it should actually become false, obviously, because as you can see, like under this character, it's a dot again. Part 1, 9 milliseconds, part 2, 7 milliseconds. Whoa, fast. Yeah, maybe I'm going to take more actually, because, you know, Python and stuff. So every time we split, so that means I should have a counter, right? Total equals 0. Or like counter, I suppose. And when we split, we plus equal 1. And what was that? Attack and beam is split a total. Okay. Okay, let's see if this is actually good. We return. And we run. Okay. Okay, it's starting well. Okay, wait, this is just the first one. This is just the... Oh, right. This is because I have to check for the first line and for the character. I guess I can just compare with this then. I guess in Python it actually doesn't matter. So this is 0, I knew it. I knew it, the result was 0. That was a trap. Hello, Jane. I was banging my head against the wall with day 7 part 2 because I had the right ID, had an implementation error. I dismissed that solution as wrong and kept trying other stuff until eventually came back to the original approach hours later. Oh, yeah, I feel that. I actually had a problem during one of the previous days when the results wouldn't be right, and it was actually because the input wasn't right. I didn't copy the input correctly, and yeah, that happens, right? Like we all have our stupid moments, I guess. But I guess that's, a skill that we can master, like the art of debugging, the art of always doubting yourself. Don't trust anyone, even yourself. Da 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 da. That kind of stuff. So yeah, we continue. And counter equals 0. Oh. Oh yeah, here. Okay. So I should have something there. Next beam. Wait. Oh. Oh. Yeah, I mean, this is next beams, not beams that we happened to. So yeah, it should be better now. So what is it now? Please. Okay, it's still 0. Let's debug. Let's debug again. One. I actually don't. Oh, yeah. Actually, no. Yeah, this is pretty useful. Like to see the numbers directly without having to put the mouse on that. Really useful. So 1 we clear for every beam. So beams is this is empty. What? Oh, because I don't do a copy, is it? Oh, okay, I have to do that, right? Yeah, okay. I have to set to a different value because in Python it must be considered to be the same object. And then the two variables point to the same array. And when I clear, then this is just clearing. Okay, 7. So what actually? So what? Um, ah, let's just put the print maybe. Print beams. Oh, so that's always an array of 1. Huh. Huh. But we're supposed to left, right, different oh, not different variable, that's why. So right plus 1, yeah. Yeah, that's a kind of stupid mistakes, right? But we get used to it. 17. This is a lot better. 7 7 6 8. Oh, wait, so let's 7 7. We start with 7 and go with 6 8. So wait, 6 8 6 8. Then we have 5 7 9. So this is working. The hash table is working. Elements are only there one time, and for now it's working well. So 5 7 9 5 7 9. Then we have 4 6 8 10. 4 6 8 10. 3 5 8 9. Wait, 3 5 8 Wait. Oh, there is the one in the middle. Uh, wait. So we have four. Okay, that must be the one I'm not handling correctly. So 4, 6, 8, 9. 4, 6, 8, 9. This is good. I'm keeping the 8. Notice. So this is good. But wait. 4, 6, 8. 4, 6, 8, 10. My bad. Wait. What? Yeah, 4, 6, 8, 10. So this is correct. But then I have 3, 5. This is correct. I continue to have the 8, so this is correct. But I don't have the 7. This is the 7 I'm missing. I have the 11 there. The 11. I have the 9 and I have the 11. I have the 8. But I don't have the 7. I should have the 7. So what's wrong? It's probably because of this one. Lookup table. Oh, this is I left beam. This is the wrong one. This is actually I beam that I want to put here. Yeah, okay. Should be good now. Yeah, just a lot of, very stupid mistakes. And can it count better than me? Yes, it can. Good. So let's actually, yeah, on inputs this time. Yeah, this one was actually quite fast. Like half an hour. 1499. Submit. Here we go. Okay, first try. And I just actually before part 2, we had yeah, Fog, who said that he did it in 9 milliseconds. So I actually want to measure this, and I'm just going to go to a previous day for that duration. Import time. I mean, I think we probably have something similar anyway, so shouldn't be that different. Or maybe I'm going to be slower, probably. I don't know. End minus start. Results. Let's try. Wait. Time. Yeah. I think there's a problem. What's that? Instant. This is just actually a lookup table. A solution for part 1 ran in 39 microseconds, but I'm using a compiled language without a garbage collector, so they're incomparable. Yeah. I mean, I wouldn't say that. I would say that I could pre-allocate. Like, for example, I have those lists, right, that I could pre-allocate. So in that case, it could be comparable. But yeah, I have an interpreted language. Like Python is interpreted, not compiled. So it's going to run slower anyways. Because yeah. Because I mean, even in like C++ or C, you have to allocate and deallocate, right? So I would say actually that in languages with a garbage collector, it can actually be faster, because the garbage collector is like freeing the memory like regularly, but it might not actually be inside the moment where we measure the function. But in your case, if it's like C++ and you free your memory and allocate it during the function, then it's actually going to count towards this. But in the case of a garbage, well, if there is a garbage collector, then it's going to count like at the end of the program. I'm using Clojure. So, Java machine, virtual machine. If my solutions run in less than 20 seconds, I'm happy, lol. Okay. Yeah. I actually don't know what closure it is at all, so I'm just going to check that. Oh, okay. You know, I mean, basically, every time I see a language like that is like kind of functional, I'm thinking to myself, like, who uses that? Like professionally, I mean, because you can use it like, for um, problems and, like as some kind of test and all of that, right? But professionally, uh, like at work, do you use that? Oh no. Okay. The haters were not, they felt compelled and forced to drive on the side of the road they were not comfortable with. Scared them. Oh, additional stress. Okay. I mean, because basically when I see that, uh, wait, when I see that, I mean, I think about, for example, well, in C++ or like, well, yeah, in C++ you have Unreal Engine widgets. No, not that. C++. How is it? It's not. Mm, I actually have to check it. It's very important, believe me. Nemo. Yeah, it's a list, so a bit hard to read if you haven't before. We use it at work for our microservices. Yep. Oh, I use F sharp, another functional. Yeah, I actually haven't used that many functionals. Something with lots of lambdas or something. Uh, not necessarily lambdas, but yeah, you can, yeah, yeah, you have lambdas. Um, yeah. Wait, what? C++ make a widget, let's say. So UMG, C++. Um, nope. Yep. This is not a widget, but this is. It has a name. It has a name. Believe me. Widget 3 Ubiton. S widget. Yeah. This is close. C++ create widget. Uh, S widget. I okay. Maybe I'm not going to find it. Wait, because I know if you look at the code from GitHub, let me actually. I guess I have to log into my account for that. Unreal Engine. Unreal Engine. If I search, let's say we have. I actually. It has sound S widget maybe. Something like this. Okay. Okay, here you go. This is functional, right? Is it? Actually, maybe wait, actually, this is not supposed to be. Do you actually. Well, actually, it kind of is. I would say. Uh, yeah, to me it's functional. A bit, yeah. It's function chaining. Yeah, I know, but the function chaining is used in this case to, like, is enabled is not set on selection change, right? Like basically every object is returning the first object, so it's as if you had arguments every time, right? Hahaha. Like all of that is well, this is the argument for this, right? And then in this function, you have other arguments, so it's kind of functional. And then same here, you have your function and you have, your argument. And, you have basically kind of the same for your slot. Um, so, well, to me, it looks like very much kind of functional. Um, I mean, it's like a bit different, right? But my point was just that in C++, you have the freedom to do functional or to do, imperative, I feel like. And yeah, thanks for the follow. It's same. I could send you my part one for this problem if you wanted to compare. Oh, actually, I'm kind of interested about this. If you don't mind, then yeah, sure. And yeah, maybe next year I'm going to use a functional language, or maybe Rust. But I really don't want to to code in Rust. I prefer using a functional language rather than Rust. Yeah, I know. Um, I don't know why I don't like Rust that much. The syntax just looks weird. Like, I mean, the thing is, I could say that about anything, like about any other language I use. I mean, okay, no, it looks even worse than what I thought. Never mind. Okay, okay, yeah. Place bean. Oh. Do, do, do. Rust is what I've been doing. AOC in. Oh. Rust is not a pretty language. Most of that file is just getting and passing data. Solution starts at 22. Yeah, basically my ideal language would be like a C++ that actually has a good library, like standard library, and that doesn't have templates the way it has with like SV9 and that kind of stuff, and that has like stuff like C#, you could say, like JRX, kind of clean, right? And what else could I ask for? I guess this is actually a lot already. Yeah, I mean just a C++ with a good templates. Oh yeah, a good standard library and a good library like package manager. Like without using CMake and something like standardized. I tried to use Rust, finished 3 days without. Uh, finished 3 days, but I cannot cope with so many symbols and compiler strictness. C# has the best standard library of any language I've ever tried. Yeah, I agree that C# is just like the standard library is just like so good. Like Python you can do pretty much like a lot of things too, right? But some stuff are like there's some there are some weird things. Like C# is like pretty uh like like if you're searching for a function, you know where it is and how it is called, right? Like count or length. When in Python you have to use the len to get the size of an array, like for whatever reason. But yeah, and yeah. So you read the file. Yeah, this actually looks imperative to me because okay, you read, but then you go from up to down, right? Oh no, this is a function. Wait, no, this is not. Okay, you define, okay, no, yeah, this is a variable. Yeah, and then you use this variable, points, you split, start, you get, and okay. Def is variable, def n is function. Yep, okay. Yeah, okay, makes sense, def n. Last one, oh, yeah. Yeah, I feel like there are like too many parentheses. Like, I guess something I don't like in, for example, Godot or Rust, like in GDScript or Rust, is that uh, in Rust, yeah, you know, you could say that you can put like the type is optional, right? But I mean, it's not really optional. Like you have the let. Um, but what I was searching for is like I want types, basically. I want types. Like, and what I want is replace the let's by the type. Yeah, let me GDScript. Yeah, okay, I can't find any good example. Yeah, okay, I think I got it. Yeah, here, right? Yeah, this, for example. Instead of putting var every time, let me replace the var by like string, or like var by vector2, or like var by float, because it's like, why do you add things? Why do you add words that you have to put for nothing, for no reason? C# is my language of work for already 15 years. Well, I love it, but nowadays it got so many features. You can do the same in 20 different ways. Yeah, I agree. And a codebase becomes messy if team changes members. Uh, yeah, I can understand that. Yeah, I can see that. So yeah, thanks for the code. And yeah, I've actually been using C# for a pretty, I guess, you know, not as long as you, but some time too, like with Unity or like for work too. Um, yeah, and I mean it's been like basically to me it's been the language that's like kind of easy, right, to use. Like, well, it's a scripting language, you know, because I'm a well video game programmer slash engine programmer, and to me C# is like the thing that if you don't care much about optimizations and like stutters, then you can use it. And like, you know, in Unreal, it's going to be used for like your pipeline, your build pipeline. In C#, it's like for your gameplay because the engine is what matters, like performance-wise. You know, in GDScript, you can use C# too, I suppose. All of that's right. So yeah, what was yeah, part two. With your analysis of the manifold complete, you begin fixing the teleporter. However, as you open the side of the teleporter to replace the broken manifold, you are surprised to discover that it isn't a classical tachyon manifold. It's a quantum tachyon manifold. With a quantum tachyon manifold, only a single tachyon particle is sent through the manifold. Wait, is it? Okay. A tachyon particle takes both the left and right path of each splitter encountered. What? Oh, yeah? Oh, okay. Oh, since this is impossible, the manual recommends the many worlds interpretation of quantum tachyon splitting. Each time a particle reaches a splitter, it's actually time itself which splits. In one timeline, the particle went left, and in the other timeline, the particle went right. To fix the manifolds, what you really need to know is the number of timelines active after a single particle completes all of its possible journeys through the manifold. In the above example, there are many timelines. For instance, there's the timeline where the particle always went left. Here you go. Or there is the timeline where the particle alternated going left and right at each splitter. Or there's a timeline where I take a poop in the bathroom. In this example, in total, the particle ends up on 40 different timelines. Apply the many worlds interpretation of quantum tachyon splitting to your manifold diagram. In total, how many different timelines would a single tachyon particle end up on? I mean, basically I just have to remove my cache, right? I mean, this is not that complicated. This is so bad. Basically, I have my lookup table, and I feel like I just have to remove my lookup table. This is so bad. I mean, I could remove the lookup table, but then I would still add numbers multiple times. So one thing I can wait actually. Yeah, one thing I can do instead is have a counter. I can have a counter. Put everything between unsafe and your most performant ever. Try coach, right? Yeah. Uh, let me actually verify if I understand things correctly for this problem, because I'm not sure. So let's say that we remove the lookup table by an integer that is first 0, except 1 for this one, because it's a count of 1, right? So you have one laser that goes here, right? So then you split, or do you? Anyway, you have a word line. Let's say you have one timeline where it's on the left, one timeline when it's on the right, and we are basically going to count the amount of timelines for each column, and this is it. So then you have this one. So you have potentially 1 1 1 1. So this is supposed to be 2, right? Because you have 1 plus 1, so 2 timelines. You have 1 here, and then you have 1 plus 2. So you just fuse that together, and you basically combine the amount of possibilities. I actually feel like I can speak a lot better English if I take that voice. Okay, I might just stay with that. Maybe not. Let me know what you prefer. So lookup table. Let's just copy all of that. Day 7 part 2. So let's call this. And this is an array of integrals now. 0. And this is basically the amount of timelines per column, timelines / possibilities. Here we go. I is 1, and counter plus equals 1. Is it? Oh no. Yeah, okay. So let's remove counter. Let's put it at the end, because we are probably going to need it, but at the end. So every time we so yeah, we just have to look at the lookup table, basically. So we have this becomes false. So what that actually means is it becomes 0 because there is the split, right? So there can't be anything there anyways. Let's put it at the end so we can actually use the value somewhere in here. So this one actually becomes I guess the initial value plus equal. So plus equal what we had already, I suppose. So this, right? Plus one, plus one. Let me verify. Boom. So you start at 1. You split on the left. So that means there is one possibility. So this is the same. So this is 0 plus 1. And this is 0 plus 1 too, so this is fine. Now this is the same if it goes here. This is 1, 0 plus 1. Same there, 0 plus 1. But if it's there, it's like 1 plus 1. It's the amount of possibilities once again. So what that means is that this is correct. But then at the end, yeah, what I don't have yet is at the end I have to add up all of this. In this example, in total, the particle ends up on 40 different timelines. Okay. Ends up. So wait, that's the amount of path, or 2, 3, 4. Yeah, okay, yeah, that's the amount of paths possible. So what we have is, at the end, we just have the amount of possibilities, right? This one, basically. The lookup table. Well, not the lookup table, actually. We have next beams. And yeah, basically we can just, we don't even need the counter. We can just do that size, like length. And yeah, and this is it. And this should be good. So let's run that. And this is, oh no, there's a duration. Oh, there's a duration. Okay, this is pretty small still. Wait, this is less than 1 millisecond. I mean, it's still like microseconds, right? But I guess for Python, that's fine. So 86, what do we have? Is this good? This is not good. So wait, this is not what was wanted? What? Oh, this is input actually. What about test input? Okay, this is 9. Okay, that was fast. So this is probably not the correct answer. So next beams. Oh yeah, because I'm still checking that. I actually should not have this test anymore, because now it's like no matter where we go, this is possible. You know, this kind of stuff. Yeah, should be good. I did like as many times as needed. So now let's try again. 40. Is it 40? Um, and this is 40, so this is correct. This was actually very fast. Like I did like 2 problems in like 2 hours and a half. Well, okay, this is actually pretty slow, but that's fine. And we have, please duration be 0. It's not going to be 0. Wait, actually. Oh. Wait. Let me think. So I do the plus, but I actually, okay, there's actually, there's actually a little something. Actually, I don't want to add it only one time for the lookup table, but I wanted to add it, well, I want to add it only one time for next beams, because with next beams, I'm only checking like the number, right? And then I'm just, well, basically I'm just getting the number and that's it. So yeah, I actually don't, if I want to optimize, I'm only doing that one time. So let's start. This is the test input, and this is 0, perfect. This is not perfect. If not, oh, I mean, yeah, because I have to look at whether this is 0 or not, right? Something like that instead? Maybe not. Check memory. I don't know how to do that. Yeah, wait. So I actually have some problem. Lookup table. Yeah, I mean, I'm always. Yeah, okay, okay. Yeah, I thought about it, but I just verified it. So here we go. 9. This is not good. Right beam, left beam. Why? Why? So wait, what did I have before that was working? I had something like this, right? And that was working with the nuts. No, it wasn't. No, it wasn't. So yeah, if I remove the nut, then I think it's working. Yep. But now I want to optimize that. And I only want to append if yeah, so this should be it, right? Like, let's just indent. Yeah, that should be it. Oh, wait, append. Wait. What's that? Oh, wait, what? Wait. Next beams dot append. Yeah, I add it every time. What about... Huh. Morning! Have a good coding. Thanks. Thanks, Pine. Sorry if I'm not checking here very often, but I appreciate that. Lookup table. So yeah, this should be fine, right? Why isn't it working? 9. I'm still adding the number, am I not? So next beams. Oh, because it's already present. It's already there. I see. It's already in. It's already in. So I guess I would have to like refresh or something. Ah. So I guess I actually want the two last things. So next beams, wait. Beams. Like previous beams. Yeah, wait, why do I want to append? I mean, I know, but... Yeah, I know where the problem comes from. It's because I have some, well, cache, right? And I'm not like every turn updating. Like basically this is the case where um, where you have this one just going down, 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 right? So like this one does not count um, in my program. I mean, in my code currently, but that, I want to fix it, right? So, so I mean, I can keep the current ones. For each beam. Does the index matter? Because I guess I could remove it. Hmm. Lookup table. It's going to be good. Uh, I mean, I can just append every time, as I said, but I don't really want to do that. Yeah, this is very tricky. Because if it's my last problem for the day, I want to optimize it. But I mean, I could actually do the to-do days day. I could actually catch up if I just ignore and just do it. But yeah, okay, I have some, I have some pride. I totally discarded it on the first day of the advent of code, but I still have some pride in me. And I do want to do it, to solve it the correct way. So lookup table. Uh, yeah, it could happen every time. And because of that, I'm missing some stuff. Wait, am I actually missing some stuff? Wait, am I actually missing? Because that was the correct result, right? If I add beams multiple times, then isn't it supposed to like kind of be bad? Because if I add beams multiple times, it's going to try running the same thing again. Wait. Yeah, but it's not recursive. Wait, how does my program work? Oh, yeah, I guess it's fine if it's like multiple times. Because we just add. Happened. Wait. Next beam. Then if there is a point, I append. Uh, I mean, no, next beam, there's supposed to be only one. There's supposed to be only one. So what's the deal? If this is different from zero, we append. But what if there is already something? I guess if this is different from... what it was before? No. If this is equal to what it was before, to last line. Yeah, okay, I get it. So basically my idea now is, here, at first, when we split, this is 0, right? Before we add the +1. And 0 is equal to this 0, so this is equal to the previous value, right? And it's the same like there. It's like this is the same as this value. So we add it one time. Yeah. But then we have potentially, the beam that continues, and we have potentially the beam from the right that continues too. So I would say that's it. That would guarantee that no matter the order, then that would be fine. So I basically have to keep the last line. I did think about that actually. But this time this time I really made it clear for myself. So we have the last beams. I guess it's actually, I don't actually have to make arrays. Last beams equal beams, I suppose. And then I just have to check if... oh wait. Yeah, this is actually not the one. This is actually the lookup table. I want to copy the lookup table. Oh no. Oh no. No. I'm going to copy the lookup table. I mean, if I'm going to copy the lookup table, then it might be like more optimized to just have all of this and, well, not all of this. My data structure here was a bit different, so I can't help much. That's fine. Thank you, Steel. But yeah, I'm wondering if it's worth making, well, we keep the previous and huh. What happened? Hmm. Hey, I didn't do it, so I can't help at all. That's fine. Welcome. Thanks for joining. What's your name? Sparkly Dark Matter. Oh, 73. So many dark matter. Crazy. But so much. I like we're in the manifolds too of the tachyon thing, and we have some dark matter. That's like crazy. We have like all the weird things of physics just gathering in one spot. Lookup table. Focus. Wait. Here we go. I have to focus. If this is the same as the last line, then we continue. But, well, we add it. But if it's not, we do not. how do we check the last line? Because right now, we are keeping it in cache. But we update it at the same time, so we need a copy if we actually want to use it. Or not. Or not. Because, my friend, we have integers with us. But we could replace integers by a struct that could contain more data, because there are only three ways that you can get to a cell, either from the left, either from above, or also from the right. So if you could store the location, the direction, like the sum that you have for each direction, then you can actually only add it like only one time without any extra cache. And this is the way the brain works. Okay. This is good. I actually found it. That actually helped me. I can't believe it. So what was I? Yeah, I was okay. My brain, yeah, Google was saying the brain in my mind was saying that we have an int that could actually be 3 ints, right? Uh, yeah. And wait, that gives us a total. Lookup table, but that means if you go to the left, then that means you have to update it afterwards, right? So basically I'm going to have, huh. I don't want to recreate an array every time. No store directions, but intersected in that solution. But interested in that solution. Oh yeah. I don't store directions, but interested in that solution. Um, I mean, I don't know if directions are fine, because if I store directions, then I'm going to have to reset it every frame. So there's going to be still the copy, right? Like the new allocation, which I do not want. Probably. So, oh, actually, because, okay, I have an idea. Because two things are not supposed to be next to each other, right? Like, if I search for this, we don't find it, okay? Because it just doesn't exist, right? So that means there's always a dot splitting them, okay? So this is actually something we can use. This is actually not a smiley. Uh, this is, well, not an emote. This is actually deeper than that. This is the wrong exercise. Um, okay, this one. So what I was thinking is, if we have 3 directions, then we don't actually have to copy it. We can just update it directly here. And I mean, what do I mean? I mean, yeah, I could just update it here. And basically I take the left, I take the right, and I boom. So basically this is going to be, oh, I don't like tuples though. Can I have like a struct? So struct. No, I can't. Class. Oh shit, this I don't like classes. Yeah, I guess tuples or structs. Okay, that's fine. So I basically have left, middle, right equals lookup table, IBM. Then what I do is, well, that's actually kind of simple. I add it only one time. So this is good. So I don't have any if, like any more ifs. And the only thing, the only difference is that I'm going to update the lookup table so that this is 0, 0? Let me think. Yeah, because there is always, like, there are never two intersections next to each other. So this is 0 left plus middle plus right, 0. So everything goes in the middle, right? Makes sense. Maybe. Maybe. Actually, wait. Isn't it going to break like everything? Like there, for example. Because there's still one thing that is going to continue going down, right? But I guess that's fine. Is it? Yeah, because I only added one. Wait, what? I guess the order actually doesn't matter. Because if this is the first one that is running, then we do left plus right and it's fine, and then we add to the left and we add to the right. Yeah, I mean, as long as we conserve, the order actually doesn't matter. If we do this one first or this one first on the same line, because it's a plus, and plus is commutative. So this is actually fine. And then we have if... Well, I guess we can just... next beams, so to the left. I guess we can actually add this one multiple times. So we can actually remove the if too. But I just have to make sure that... That what? That I mean, yeah, yeah, wait. I do the plus, so wait, I actually have to update the table everywhere. Oh no. So yeah, this is actually 0, 1, 0 because it comes from the middle. And this is going to become 0, 0, 0, right? This is 3D. This is 3D, boys. Okay. Now I can append anytime, anywhere. But I can also only... Well, actually, if I do that, it's going to add it multiple times there anyways, right? So yeah, you have to prevent it here. So let's have a left cell. Equal. Something like that. And I have to check if... So it's trying to go to the left, right? So that means it's going to add to the right one, right? And that means we have to check if the one on the right is 0 or not. This is it. Probably. I hope this is fine. So left cell, I beam, left beam, left, yeah, right cell. If yeah, so we have left cell and we have 0 is left, 1 is middle, 2 is right. So if this one is 1, well, if the one on the right, 0, 1, 2, is 0, then we append. And we are going to, instead of doing the plus here, let me put it down. Instead of doing the plus directly, we are going to equal equals left cell 0, left cell 0, 1, and this is lookup table beam, I beam, right? I beam, wait, no. wait. Yeah, actually, this is it. Hey, Progs, hey, how are you, Quinten? Hello, so many people. Okay, so we do that. Now for the why left, what? Oh yeah, I just copied it. So right beam. For the right beam, we have that. We check if this is 0, 2. I mean, I guess I had like the solution just before, so maybe I should have kept the easy solution. Let me copy that somewhere. Let me actually open a new file. And let me undo. Int. So okay, this was working. So let's copy that. Let's go back. Hey. You know, just to have the solution, right? And this is 2. Day 7, part 1 gave me hell today. I misinterpreted the text, which got me stuck for so long. Wording definitely was not very clear on that one. Yeah, I actually had something like that for something called the sandbox that I had in my college a while ago. That was like, I really thought this was good because basically this was about, basically it was some kind of problem, like similar problem in C, and there was a pointer of pointer. So this was actually something, you know, like that, right? And this was actually about arrays. And I thought it was an array of arrays, but apparently it was just a pointer of arrays. And it was basically just, you know, just so bad. And basically I got it working, but it wasn't working on the remote thing, right? The test, because yeah, and they wouldn't like help me. Today was mega confusing. I think I must have seen day 7 on Prog stream, and that got me. Oh, day today. Oh, okay. Oh, yeah. Yeah. But yeah, basically for the second part, we're doing something kind of weird, but that should be alright. We have the right cell. We check if, so this one is the one on the left, like the source from the left. If this is 0, then we append 1 time. And then lookup table So yeah, this one is a bit different too, right? So then, basically, we put the new value on the left, and this should be good. That should be good. And the new one is just 0, 0, 0. Part 2 is easy in comparison, luckily. For me, the problems were better last year. Yeah, I think like they were better. I only did a few, but they did seem better. I mean, he didn't have a lot of time apparently this year. Up to now. Yeah, up to now. Um, apparently. Let's give it a try. And yeah, basically the second was easier, but I'm trying to make it like optimal, right? Can only concatenate tuple, not int. Left plus middle plus right. So what's the deal? Can only concatenate. Wait, what? Wait, let's try again. What's the deal? Tuple. What is left? Oh, left is a tuple? Oh! What? It can't be? 0. What? What is that? Can't I? What? Oh, I guess it's because of... Oh. Is it because of that? Like, tuples... Okay, I think I get it now. I get it. For good. I don't. Yeah, why is it a tuple? I guess it's because I... Today's took me a long time to get my data in a good state to actually solve. Oh. Yeah, I still have to check today. I actually don't know what this is about at all. Lookup table. So yeah, how do I split? This is so stupid. Is it like something like variadic in C++ like this? Or maybe something like this? I'm maybe it's going to listen to me and solve all my problems if I ask gently. Python. Split into split tuple into variables. Boom. Here we go. So yeah, this is it. This is supposed to be how it is. If the number of variables does not match... I mean, no, this is supposed to be... Yeah, this is supposed to be good, right? Am I doing something wrong? Because if I look at the list, it's just a list of tuples, right? So this is like, what? What's this shit? What is this? Oh. Ew. This is why. No, this is not why. Lookup table. Let me check again. So what do we put in here? We have to be careful about what we eat, right? Left beam, left beam. Oh, that's why. Right beam. Here we go. Should be better now. Or not. Yeah, okay, maybe it's not possible actually. The right is multiple, right? Yeah. Wait, actually, it's only one. But is it? Yeah, it's just the test input. Oprox doing the tree one. Yeah. I'm doing this one. I'm still on yesterday because I didn't actually do the problems this weekend. So, you know, I had to do like the one from Saturday and well, the one from yesterday. And I'm trying to make this one like kind of in an optimized way, like to preventing repetitions. Which can be kind of hard. If 0, then we append. Yeah, so maybe it's because of this one actually. Wait, so basically there is left, middle, and there is one that is a tuple. So the question is, well, we have to find where that comes from. And I think I found it. Because we have the lookup table, but inside the lookup table we have a tuple, right? So, oh. Yeah, I mean, this is it. Yeah, I mean, this is simply it. So the left cell. I guess it's just 0 in this case, right? Let me just check the input again. Yeah, this is fine because basically every line. Yeah, okay, this is good because of how the data is. Probably. So lookup table, and this is 1. This is the one in the middle that we want, and this is it. Please. 17. Wait. Was that the correct one? Wasn't 20? Wait, it was 20? What was it? Okay, this is supposed to be 40. Yeah, this looks kind of bad. Good luck, mine took 200 milliseconds to compute for day 7.2. 15 microseconds for my part for day 7. Yeah, this is crazy. Wait, what? So I look up on the right, and the source is the one currently here. Then why left cell? Why left cell? This is actually so stupid. Why left cell? Oh! Oh! Yeah, this is supposed to be right cell. And now this is 20. And now we just do a ×2 and this is good. But I don't think that's how things work, sadly. I think we might have to debug now instead of just looking at the code. Maybe let's print. Yeah, first let's print beams. That was fast. So test. Not this one. Test. 7. 7. 6, 8. 6, 8. 5, 7, 7, 9. Okay, this is actually kind of wrong. That actually proves me that this is wrong. Because I have it 2 times. So that means my optimization is not working anyways. Wait, what? Left cell equals 0. Wait, that's so stupid. Oh no, never mind, it's 2. It's 2. Yeah, it makes sense. But I mean, yeah, it's going to be 0. Of course it's going to be 0. So I guess the question is actually if this and... Well, actually it's actually the others that matter. So this is like if that equals 0. Well, if this is different from 0 and this 2. So yeah, this is basically it. And this one is 1 and 2. And different. This one is 1 and 2. But this is a right cell. Okay, now it's going to be optimized, but still not working. As you can see. Great. Okay, so basically we start at the correct number, but then it doesn't want to happen. There's a problem with that. Yeah, I can remove the last beams. So... last beams. It never happens. So basically, we go down, we see the thing that splits, we check the left cell, so we try to add on the right. The right is 2, so this is why we put it here. And if the other ones are 0, if they are 0, we append. Because basically if there is no ray already there, then we append. Because it's not going to be processed if we don't. And same here. So wrong condition. I was actually fine at the beginning. Okay, 9. This is fine. Debugging little by little, right? So we start at 7. Then we go 7, 6, 8, 6, 8, 5, 7, 9, 5, 7, 9, 4, 6, 8, 10. This is correct so far. 4, 6, 8, 10. Okay, so let's go there. 3, 5, 7, 8, 9, 11. This is correct. This is correct. And then 7. Yeah, this is correct. Then we have 2, 4, 5. Wait. No, it's 6. Yeah, this is good. 7, because it continues down. 8, because it comes from above and from the right. 10, 12. This is actually good. And at the end we have 0, 2, 4, 6, 8, 11. Wait. 10, 11, 12, 14. Wait, let me count again. 0, 2, 4, 6, 8, 10, 11, 12, 14. So this is actually correct. This is actually correct. It only counts one time now. The only problem is the sum. The sum is not correct. And this is because I returned the length of next beams. Oh wait. Oh no. Oh no, I'm so stupid. Wait. Yeah. 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 Because I haven't actually processed it. Because before, I happened it like every time there was a new possibility, right? But this time, I actually have to make a loop. Because I have to add all the values, all the possibilities together. So this is actually correct. And I'm not going to loop on lookup table. I'm going to loop on next beams. So we have beam in next beams. We have basically not sum, total equals 0. Total plus equal beam 1. Add the center. And we are going to return the total. Here we go. And this is it. Start. And this is going to be it. Or not. Shit. So wait, beam is actually... Oh yeah, because I have to look in the... I have to look in the lookup table. Incredible. Here we go. Double array. So we have the beam that is an index. We look in the lookup table for O1 access. We retrieve the tuple. We get the 1 because at the end there is, a line full of points. So we can just get the 1. Well, so basically, it computes this part. So this goes in the middle. So we can just add what's in the middle. And this is it. And this is it. 40. This is correct. And this is for the first, well, this is the test input, right? But for the test input, it's like 1 millisecond in Python. Well, 2 if you round up. And what about the input? Because, yeah, okay, let's try. I think it's going to have... Oh, this is already finished. This is actually 22 milliseconds. So this is not as good as the 15 microseconds from Stain, but but yeah, this is still all right-ish. How did you... Wait. Because Quinten told me about his thing, I think. This one has been string manipulation, Deluxe. Oh, I didn't say that. Yeah, anyway. Yeah, what was your scores? Because wait, I actually haven't submitted it, but I think this is correct. And this is the right answer. And now I want to check. So this is basically 0 to 0. Well, 0 to 2. Okay. What if I check with the first version that was not optimized? Zero, 0 to 2. Okay, yeah, this is longer. Okay, this is definitely longer than that. Yep. I have my thing. That's that. Okay, yeah, this is like very long. Yeah, my computer is actually dying. Wait, is it like an infinite loop or something? No, it shouldn't be. Wait, that's crazy. Can I send you what my data structure looks like for the example data in part 2? Yeah, sure. Go ahead. Yeah, I'm actually kind of interested in like Stein's solution. I guess it was C or C++, right? Though. So I don't know how much it's impacting all of that. I guess I have to. Yeah, like what's long in my code right now? Well, this is crazy how long it's looping. Because it's not, yeah, it's not infinite. I do a +1 at the end. So it is going to stop at one point. 86. But yeah, this is crazy long. Yeah, okay. Basically, I did the right thing. And this was the way to go. The 2-2. Or like one of the ways to go. I guess it actually would have been more optimized if, you know, there was more empty space, I think. Like the more empty space there is, the more my solution is optimized compared to other solutions. Basically, the solution of just looping through every point. Problem though, we are comparing apples and oranges. Nobody has the same hardware and language kit. Yeah, you're right. I'm actually on a laptop streaming at the same time, with my stream and the music playing. I mean, there are still different CPUs, right? I guess I'm on a laptop though. So for part 2, I did a much simpler solution. You only need a row of integers to count the possible path. I reused the bottom row from part 1 and assigned each beam present a value of 1. When you walk the grid from the bottom up, adding the left and right cell into the middle every time. Yeah. Wait, what? The total was then summed into the position of S. Wait. In the top row. It was summed in the top row? Wow. I kept a hash map of points to the number of beams on the point. Yeah, this is basically, well, the hash map is basically what I did, but instead of a hash map, I made the lists so that it was O1 and not amortized O1. So yeah, this is basically a hash map. My lookup table is basically a hash map. This is, just not a dictionary, but this is a hash map. Well, I guess no hash is actually computed, but yeah. For Patriot, you only need a row of integers to count the possible paths. Yeah, that's what I did at first. But then I had a problem because I added things multiple times, right? I reused the bottom row from part 1. The bottom row from part 1 and assign each beam present a value of 1. Wait. Then you walk the grid from the bottom up. Oh, then you walk the grid from the bottom up, adding the left and right cell into the middle every time you hit. Oh, this is actually a good idea. Yeah, what if you go from bottom up? Let me look at. No, let me look at that. No. So what was the first actually? So basically, you add 1 every time. Well, you add 1. This is the amount of. Anyway, you have this. Okay, you have the outputs there, and then I guess you go up. but then you still have to go right or left, right? I guess you can just check what's on the side. And then you can just add. What? Spoilers on mine, I did this one recursively and stopped the recursion in between each death, so I could kill the duplicate promises and add more strength to the one. Huh? You'll see what mine looks like in the paste bin. Okay. Oh, paste bin, so many paste bin. Oh yeah, I actually didn't check the previous... Maybe I did check actually. You guys not using GitHub repos for AOC? Oh yeah, I could paste my GitHub if you want. Mine is not public. Look at the paste bin. Okay, here we go. Do 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 do. Oh. Ew, Rust. Okay, so you have. Wait. Yeah, okay, this is input. Path 2. So path 2 is yeah. So you get a reference towards an array of characters. Let's say an array of arrays of characters, maybe. Anyway, path. Wait, what? Is it? Input. Parse input. Yeah, okay, so that's actually one difference. Wait, is it? Basically, what I'm thinking is that you are passing the inputs outside of the recorded time, which I guess I'm reading the file, but like, for example, the split lines is inside, right? So I guess that's a difference. That makes it faster for you because you have it outside of the recorded time. And yeah, you have like a whole loop, right? So I mean, I'm sure it's going to take some time. Yeah, what's actually my time if I remove that? Um, like maybe not that long. I don't know actually. So do you include the parse input? No, you don't actually check stuff. The passing takes 63 microseconds. That's so much. Well, I'm kidding. Yeah, I mean, I'm probably going. I mean, I'm definitely going to be longer than that, right? Oh, not this one actually. But yeah, I just want to check. I'm kind of curious. So there. Then we have, let's say, this. And we... Oh, wait, I recorded with the debugger, right? I ran the debugger to record the time. That's so stupid! If I want to record, I actually, without the debugging is better. Okay, wait. What was it before? Wait, I'm actually printing stuff. Yeah, I guess it's taking some time too. Okay, yeah, I don't know why I'm like trying to make my program like slower. Okay, now this is 1 millisecond. Yeah, okay, so this is getting closer. Yeah, definitely. What did I have before? This was for the tests. So yeah, this one was the real one. And it was like 20, okay, so from 20 milliseconds to 1 millisecond. Yeah, okay, I guess that's a big improvement. Okay, but yeah, your solution, the rest. What was it? Part 1, part 2. Last input, unwrap, enumerate. That's the printing. Yeah, definitely. Definitely the printing. Yeah, that was so bad, the printing. So that's what you do. I don't understand the rest. No, actually, wait. Okay, so this is a type, but for some reason this is now a variable, right? Okay, this is fine. So if this is this, then 1. Oh, so yeah, you basically go from here. Wait, what? Oh yeah, that was your input. That was your input. Because I mean, okay. Oh, wait, no, that wasn't. Wait, no, because you need the you need the you need the final one, right? So did you modify like the map, the array? So wait. So okay, you change it, right? You modify the inputs, and since it's a reference, you reuse what was on part 1, as you said. Part 1 does this by mutating the input. Yeah. So that means when you're recording your part 2, you're actually not recording part of the problem. What's the total combined? I guess it's still, small. But yeah, I'm kind of curious about what the total is. Like if you add part 1 plus part 2. Let me still check. Actually, this one match. If this is this, then wait. S. If this is S, then the next one is this. And if this is this, then you do stuff. And yeah, okay. If the next one is... So yeah, you have a double loop though. Yeah, so that's the slow. 63 microseconds passing. Part 1, 42 microseconds. Part 2, 15. So I guess I removed the passing too, right? So I guess if you add up part 1, part 2, that's like, yeah, still like 57 microseconds. Yeah, that's nice. But I'm thinking maybe if you have like a double loop, maybe you have some cache optimizations, well, some like cache improvements because of that, because you just go, you loop, right? So that can be a nice thing. You don't have like, well, I guess you do have some ifs and matches, right? But yeah, I guess for long things, I still do think this is that keeping a list is better, right? Um, wait, what was actually my beams? Next beams, lookup table. Yeah. When n grows, this is definitely better. But I think I guess it was fine for the input and what. And I mean, yeah, I think it's a like nice way actually to it's, I feel like I would say that's some kind of Minecraft way of doing things. Like, in Minecraft you have like voxels and you have to check for each block if you have like a block next to it. Like, if you want to update water, then every frame, well, every tick rather, you have like an update on every block of the chunk, checking if there is like a block of water next to it. And this is exactly the same logic, right? And this is working fine. Actually, I'm not sure. Um, because you can also have a list, right, stocking like the water. But no, I guess in Minecraft, since you have like that many blocks, then this is actually your way of doing things would be better for Minecraft. I think I was the only one doing backwards. Yeah, I wait. No, actually, Stein just did it. Just we're looking at his code, and he did it. Yeah, part two. You have the last things. So you have the last line. For every character, you check if this is the thing, right? If there is a beam. If yes, then path index is 1. Okay. Okay. And this is -1 by default? I don't. Anyway. Then you 4. Oh. Oh, what? Wait, what? So you do go through every element again. You do go through every element again. Yes, same I did. But you could just what? Actually, I did it a bit more different, I suppose. Uh, wait, let me think. Yeah, I don't remember what I wanted to say, but uh, I thought many did recursion with pauses for part 2. Yeah, because I mean, um, recursion is actually very funny because that's like a concept. Well, basically, people that start programming uh, don't know recursion, right? So like, they're kind of bad at it too, right? Like intuitively, I suppose they don't have a lot of intuition for recursion. But then when you get better, you have, well, when you get good, then you know how to do recursion because you made, for example, recursions for trees or like search functions, like some stuff, right? Fibonacci, I don't know, like mazes, of that, and you get good at recursions. But then you realize actually that recursions have a worse performance than iterations. And that's when you start converting your recursions into um, stacks and I guess queues, depending on what you do. Or like a state machine. And you go like for, um, how is it called? Death and birth. Wait. Death. I forgot the name. Maybe someone is going to tell me. Okay, so recursion, death, breath. I don't know. Oh, breath. And BFS. Yeah, breath first search and death first search. And you can actually, you can do that with a recursion pretty easily. But if you want to replace that with, an iterative solution, then you have a stack or a queue for each other. When you say poses, I assume you mean memorization? Oh, yeah. Yeah. You know, the input produces output X, just return X. Yeah, memorization. I think it's what he's saying, yeah. I actually thought he meant, like stuffs. But yeah, that's probably memorization. How is it called also? Because there's memorization and that's... Wait, there's tabulation? Memorization. How is it called? Because that's for dynamic programming, tabulation. And yeah, the bottom-up approach is tabulation. I mean, in a way, what we did was actually tabulation. But the problem is that this is not a tabulation problem. This is not a... Well, this is a dynamic programming problem, but not this kind. Because of the spaces, basically. I guess this actually depends, like, if you have like everything close together, like in your inputs, then I guess this is the best solution. If you have everything far apart, then this is not the good solution. I mean, I guess it all depends on the input, but I mean, we just have what we have, right? But this was, thank you a lot for sharing me all of that. I appreciate. And yeah, so many different ways to solve things. That's kind of great. Let me... Okay, yeah, I'm going to remove the print. Let me just remove this. And here we go. Maybe should I... It's like 2 a.m. Should I look at the next one? At least. I feel like I'm going to try finishing it. So I did submit it, right? Yeah, I did. Day 7. Okay. Maybe we can try speedrunning it. 1 hour and a half. We can try that. You thank the cephalopods for the help and exit the trash compactor, finding yourself in the familiar halls of an off-pole research wing. Based on the large sign that says Teleporter Hub, they seem to be researching teleportation. You can't help but try it for yourself. Wait, I already did that. Technically, there is no need to go bottom-up for part 2 like I did. You could do the same thing, top to bottom, by splitting instead of consolidating. Yeah. Yeah, that, I actually thought about it, but then I kind of mixed it up with my solution, and yeah, I guess that's what I did. Not really, just get all the steps for next death and filter out all dupes so I can add more strength multiplier for path. Oh, just get all the steps for the next death. I filter out. Oh yeah, okay. I think I get it. Maybe not. Anyway, and yeah, that's a nice point. Well, you can actually, yeah, that's a nice point, Fog. You can actually just do it, and yeah, I actually didn't take it into account. But then you also have the memory issue because you have, you know, the delay, right? Like the speed. You have the speed, but then you also have, like, basically, if you do that, then oh no, never mind, because you overwrite the same array, right? Well, yeah, you write in the same array. So I guess that's fine. Yeah, that's fine. Never mind. Mixed my code earlier. Oh, but I really doubt it's a mainstream approach to solve the problem. Wait. Oh yeah, you did. My bad. GitHub. Oh, fuck. I didn't see... Wait. Fog, blackout. Wait, I actually didn't. Whoa, whoa, so many. Ah! Wait, I actually saw this one, right? No, I didn't. I didn't. Quantum Tachyon manifold. Some crazy languages you have here. Down. And you go down, down, down. Yeah, okay. The loop. What about this one? From Frentis. Comments. Slow. Naive. Wait, this is actually so short. Oh, this is only the second part. So you pause. If this is this, then splitters ignore. Wait. What? What? I feel so lost right now. Wait. Was it? Blackout? Okay, here we go. Oh, so, oh, Quinten, okay. Okay, okay. So, yeah, this one is like so short. Beam map. Oh, array 2D.init. So I guess you're building a new array. Oh, and you match. Okay, so basically you're initializing an array from a lambda that is taking the row and the column, and you match everything, and you boom. This is crazy. This is crazy, and I don't understand anything. Oh, can't I? Oh, okay, never mind. Yeah, this was just to parse. Yeah, I mean, okay, makes sense. Oh, this is some. Oh, okay. This is some dynamic programming because it's called DP, as you can see. But this is basically just the 2D array. So yeah, I mean, in a sense, I did DP too. I did DP. The only thing is that with dynamic programming, you don't have to store the whole array. You can just then, cache the last line. And that's what I did. I cached the last line. But then, well, for the first problem, but then for the second, I had to store like the directions so that I could prevent multiple, you know, numbers, let's say. Jacob. This is so short. Get next being frac. I guess, yeah, that's thanks to functions. Wow, functions. I don't know what this is, but this seems like pretty great. Yeah, Quinten. Let me check. My rep output probably makes more sense than the closure code. Quantum is the one for part 2. F sharp. Ignore just avoid the function to return, so it can continue. Yeah. Yeah, Quinten. Tachyon. Do you have a dictionary this time? Down, go. Oh, this is JavaScript, right? I was thinking, what is this language that looks so weird? Is it Go because there is a Go here? No, this is not Go. This is JavaScript. No, this is TypeScript. This is TypeScript, actually. TypeScript. So that constructor, down. Oh, down is... Okay. And if... Yeah, okay, so yeah, you do have some memorization. This is memorization, I suppose. But in a way, you could say that I didn't. Well, I guess I don't have a recursive, so I didn't do memorization. Uh, this is cache in my case. Which go where a wrapper of closure? Down is the most important function. Go is a wrapper function. Yeah, because the promise is I was tired. And yeah. Down, down. So yeah, I think the recursive approach is actually pretty, how do you say that? Elegant. I think this problem really has a good recursive approach. And I think your solution is actually, faster than the others for like large arrays. Similar to me. But what is, well, is it actually a dictionary? Yeah, it is a dictionary. It is a dictionary. It is a set. Okay, that's a set. So you know what that means, right? You know what I'm going to say. No, but that's fine. Sets in TypeScript are tuples. Oh, so maps. Wait, no. Okay. Um, but yeah, I guess one problem I have actually compared to you, you just can't have duplicates. Yeah, that's a set. Yeah, I mean, yeah, makes sense. That's the same as a hash map, but well, this is a hash map. It's the same as a map, but uh, with no values. Uh, but by no duplicates, that's for the keys, right? Not the hashes. Um, and and yeah, this solution is actually better if you have like a big array compared to mine, because I instead of having a hash map, I settled with a list, right? So I have like a lot more memory that I'm storing up. Well, I guess it kind of depends. Uh, Basically, if the array grows bigger and bigger, you're going to be very good memory wise, but I'm going to use up a lot of memory for just a little extra speed. That might not be worth it. In that sense, would Clojure be a wrapper for Java? And Java is a wrapper for C++, is that it? For C, sorry, for C. But yeah, thanks for all of your solutions. Yeah, definitely. Basically, I think there are three different algorithms that are the best in their own categories. The first one is you loop through everything the Minecraft way, and this is good for like small arrays with a lot of intersections. Then you have, I guess, my approach for arrays a bit bigger. Well, for bigger arrays that require a lot of memory, but that is still fast even for large arrays. Like that is actually the fastest for large arrays. But then you have Quinten's solution with hash maps or like sets, where it's actually better for memory, a lot better for memory if you have like giant arrays, because mine is just going to explode. And yeah, and that's three different solutions that all of them have their pros and their cons, and that's like pretty sweet, pretty nice. Yeah, I needed that because I was OOMing on P2 initially. I OOMing. Oh, object oriented. Anyway, next. H. Ah, out of memory. Okay, okay. Well, I guess. Okay. That's why my part 2 is so different to part 1. Uh, oh, you actually didn't see it. But I'm gonna trust you. I mean, mine is pretty different too. Well, I guess it's still, no, actually, it's actually the same. principle. Never mind. Playground. Equipped with a new understanding of teleporter maintenance, you confidently step onto the repaired teleporter pod. You rematerialize on a non-familiar teleporter pod and find yourself in a vast underground space which contains a giant playground. Yay! Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project. Through careful rigging, they have suspended a large number of small electrical junction boxes. Their plan is to connect the junction boxes with long strings of lights. Most of the junction boxes don't provide electricity, however. When two junction boxes, so many wait, 25 times. My God. Okay. Oh, however, when two junction boxes are connected by a string of lights, electricity can pass between those two those two boxes. The elves are trying to figure out which boxes to connect so that electricity can reach every junction box. Yeah, not boxes, box. They even have a list. Wait, 31. They even have a list of all of the junction of the boxes position in 3D space. 3D space as an input. For example, this list describes the position of 20 boxes, one per line. Each position is given as XYZ coordinates. So the first box in the list is at these coordinates. Got it. To save on string lights, the elves would like to focus on connecting pairs of boxes that are as close together as possible according to straight line distance. Yeah, that's Euclidean distance. In this example, the two boxes which are closest together are this one and this one. Okay. By connecting these two boxes together, because electricity can flow between them, they become part of the same circuit. After connecting them, okay, I think that there is an algorithm for that. I feel like it. After connecting them, there is a single circuit which contains two boxes, and the remaining 18 boxes remain in their own individual circuits. Now the two boxes which are closest together but aren't already directly connected are this one and this one. After connecting them, since this is already connected to another box, there is now a single circuit which contains 3 boxes and an additional 17 circuits which contains one. Yeah, okay. Next to connect. After connecting them, there is circuit. Okay. Next to boxes. No. Because these two boxes were already in the same circuit, nothing happens. Oh. So far, my only experience with interrupt is integer/parseInt. You can also call math, like math, pow, etc. I have a lot of experience with interrupt between TypeScript and anything else. I actually don't at all. I think. I actually don't know what that means much. What does that mean? Okay, I guess it's not something from Tokyo, right? Programming. Oh yeah, that. Okay, never mind. Yeah, I actually have a lot of experience with that. Never mind. Like running C code from TypeScript. Yeah. I actually run C code from Python. I run Python from. No, I didn't run Python from C++. What did I do? Well, I actually, is that it? Yeah, I ran C from C++. I ran C from C++. That's, very good interrupt. I'm like so talented. No, no, I'm not. Uh, this process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. Wait, what? Oh, okay. They would like to know how big the circuit will be. After making the 10 shortest connections, there are 11 circuits. One circuit which contains 5 boxes. One circuit which is actually... Okay, I actually know the algorithm for that. There is something called disjoint union set. But actually, can you actually use it? But this is basically to solve this kind of problem. But I'm actually not very sure, because you need connections for that to be nice. You need an array containing connections. And you don't have them here. Yeah, this is actually not that. Na. 7 circuits, multiplying together the sizes of the 3 largest circuits, and one of the circuits of size 2 produces 40. What? Okay. The list contains many boxes. Connect together the 1000 pairs of boxes which are closest together. Okay. Afterwards, what do you get if you multiply together the sizes of the 3 largest circuits? Actually, I think you can use disjoint union set, because this is a group. You just have to find an optimized way to find boxes that are close together. And for that, you can actually use a grid, for example, to have some kind of hash map in 2 dimensions. Well, in 3 dimensions. Well, I guess in 3 dimensions it might be a bit more, like a bit different, because I mean, it's 3 dimensions. You can still do that, but it means that there is going to be more empty spaces probably. Other than that, we can have an octree. We can also just sweep. Like, basically sweeping is, instead of checking every element with all of the others, what you can do is sort every point by, for example, the x coordinate, and that way you yeah, actually, I don't know. I mean, this is fine if you have AABBs, I suppose. Yeah, can we do AABBs for this one? Because we're checking like the distance between points. The points themselves don't have like coordinates. Well, coordinates, like, they don't have a box, right? So my question is, can we actually... Because basically, well, we are basically going to generate an AABBs with spheres, you could say, if you just do it naively. One Gemini6 member rendered the simulation in D3 and manually counted the answer. AABB, don't overcomplicate it. Yeah. I mean, what I'm saying is that we are doing it without really realizing when we take the naive solution. What's actually the... Wait. What's actually the puzzle input? There's still like a lot of numbers. Should I keep it for tomorrow? It's like 2 a.m. and a half. But what can we do? Because this is special. You need special partitioning. uh, for it to be optimized, and that's a hassle. So I guess 3D grids are like great in that sense. I mean, I would go with a grid, but that's like such a hassle. Do you have negative numbers? You actually don't. Okay. The box is infinitely small. Uh, yeah, for a point, but I was thinking about. I mean, basically, you're going to check the distance between each point, so that's like a circle, right? So then you compare this cycle with another cycle. So you have AABB collisions between two cycles, but you just don't represent it like that in your head. You compare the distance. The point is a point, no spheres. No, the distance, when you compare the distance. Because basically what? Basically, yeah. um, anyways, you really do not need a. Yeah, you don't really understand what I'm saying, but I understand because I mean I understand that what I'm saying is like kind of bullshit. Okay, I'm not. Don't worry, I understand, Quinton. What I'm saying is just kind of how to say it. Yeah, don't worry about it. Really. But yeah, what? Okay, one solution I was thinking about for grids because there seems to be like the minimum seems to be like maybe 600 actually. Uh, but yeah, I was maybe planning of taking the minimum number, the maximum number, and like trying to divide that in different, you know, um, cells, so that then you can hash it. Well, hash it, just yeah, put it directly, right, in O1. And then you can only search like the ones that are inside. And it's actually from experience, grids are actually pretty performant, like very performant. I mean, mostly in 2D, but I think in 3D they can be they take a lot of memory potentially. Actually, we just have points. Um, so I mean, yeah, why not? Should we do it? 230. Okay, is the second part complicated? What is the second part like? Like, okay, how long is the second part? Is my question. Second part took me like a few minutes. Oh, only? Okay. I mean, okay, we can try it. I'm going to trust you with my life, Quinton. Part one was the hard one because the stupid do nothing, which was in fact not do nothing. Okay. Uh, yeah. So for this part, I was planning to use this joint union set, which I'm probably going to modify a bit to do it my way because I just love this kind of logic. Disjoint union set. Maybe I don't even need something like that. Let me think. But yeah, basically, this is this thing. You bind 1, 2, and this is basically a tree. Okay, this is a tree, and that's why you can only you can count only at the end. This is pretty elegant. Like there is usually a better way, like for with less memory, but like speed-wise, it's nice. And I do like this kind of funny, like using the trees like in such a funny way. I did this from first principle, Lemo. Okay. First principles. But yeah. Okay, day 8. Let's speedrun. So we have all of this. We have the split lines. We have the counter, maybe. We have day 8. We have day 8. I said day 8. Here's my code solutions. No! Not now! Let me actually close all my Google windows that I opened. Unreal Engine, wow, no. Okay, this is my stream, I'm not going to close that. And yeah, this is basically the input, right? So let's just copy and paste. Now let's go back. We have the other input, which is this one. This input. Day 8. So we have, for each line in lines, we're first going to parse because it needs parsing, okay? So we're going to split. And this is basically X, Y, Z. But that's like strings. Ooh, strings. So then something like that. So then let's say we have our class, I suppose, in Python. Ooh, this is a point. And this is, I can't do that. X, Y, Z. So I guess integers or floats, because I guess if we have the Euclidean distance, then we are going to use floats so that we don't have to convert to like casts with floats. So let's do that. You can see the desperation in my part 1 example with all those unit tests. I don't know. So this is in Python, just X. Actually, I mean, I guess I only need to make points like one time, so point equal point. Point.x equal int. Now I can just do this. Okay. And then I have an array of points. So this is like this. And here we go, right? I can just, what is it happened? Why is it called this way? Okay, here it is. So this is ON. This is fine. This is fine. Because basically the worst is ON. So wait, for each point, you check every other point. So worst case is, oh, well, naive. The naive way is ON times N, right? Because for all points, you have to check other points. And then you can have, if you use disjoint union set, you actually have some, well, something like that, right? You actually have some amortized thing value. I think it's like, I don't remember, but it's not Abraham, it's, well, disjoint union set wiki. Ah, da, 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 da. Oh no. English. So yeah, this is amortized. So this is the same as the hash map, but the amortization is a bit different because as you can see, there is an alpha here, right? And the alpha is actually the inverse Ackermann function, extremely slow growing. So the inverse Ackermann function is actually okay. Can I first digits, well, first numbers of inverse Ackermann function? I guess we can have a graph, right? But yeah, basically you have this, and like 9 is 4, and then maybe let's have a graph. Okay, this looks like this, I think. Oh. Okay, we can't actually see anything. Oh no, a PDF. I'm afraid I should not watch that. Anyway, yeah, this is very small. This is the point. I definitely just did the naive approach and found all of the distances first and then just started. I mean, this is a way, right? But I mean, I'm trying to not just do the naive one because yeah. So naive is ONN. What I can do is first a grid, second. I mean, okay. First, let's do the naive approach. Let's just do the naive approach. But if we sort, it's O log n on top of that. So I don't want the sorting at the end. Okay, I don't want the sorting. This is my condition, and I'm going to do 4. Well, basically every point is going to have an index, right? So we are going to have basically a team, a team like group, well, point to group, because I'm going to use it like a hash map, you could say, because, well, basically instant access, right? O1. This is a list of IDs that are going to point to themselves. So this is going to be like 0 times 2 NB points equals that. So this is going to have the size of points. And basically, this is going to be ON. So basically, we are going to loop one time. For every point, we are going to initialize the array to itself, to its own ID, okay? So basically, by default, every point is going to be grouped with itself. That's what it means. And every group has an ID, an identifier, and this is it, right? Simple, right? So now what I can do is I was basically thinking a little, but that's going to be the inverse Ackermann function that we are going to use at the end. But for now, let's just do the simple naive solution, shall we? So for E in range, NB points. So then we have J. And then what are we going to do? We are just going to check, right? So let's just have a static. We can't. Def, distance between P1, P2, which are points, is going to return a flash, right? And actually, that's not what we're going to do. You know why? Because this is not optimized. Because the square root function is actually not optimized, and we actually don't need it. It's actually very slow. Well, very slow is everything is relative, right? But what you can do is actually dist squared. You can actually take the squared distance because you can actually compare the square distances, and that's it. Because if you have dist1 that is less than dist2, then you have, you know, basically this equality, right? So you don't need distances. So this is that times, actually, p1 dot x minus p2 dot x. So yeah, this is basically the delta, right? That you are going to have. X delta. Then you have y delta. Then you have z delta. I mean, yeah. Y, yen, c, yen. Here we go. And then we are just going to do x delta times itself plus y delta times itself plus z delta times itself. And this is it. We just need that. We just need that. And now we're just going to get the square distance. Actually, this square. Okay, let's call it like that. Square dist. We're going to get it between I and j. So we have dist basically. Also needs to square root for the deltas. For the deltas, what do you mean by that? What deltas? No, it doesn't. Does it? It doesn't. Because this is a squared distance. This is not the distance. This is the squared distance. So I don't need the square root. So I'm optimizing, and I don't need the square root because of what I explained before. As in, distance 1, if distance 1 is less than distance 2, then this is less than this. Oh, you are keeping it squared. Yeah. I'm optimizing. I'm going to put a comment, keeping the result squared to prevent the square roots. We don't need it. We don't need the actual distance. Maybe we're going to need it if we make a grid, for example, but that's it. For now, we don't. It's the naive solution, so let's optimize it however we can. You're just keeping it squared. Yeah. It's just moving. The chat is. So we have the distance. So what now? So yeah, let's have the mean this equals 0. Never mind. I can't. So Python max float. Oh, sorry. System.floatinfo.max. Let's do that. Here we go. System.floatinfo.max. Here we go. So this is the minimum. So there is going to be one that is less, right? So then we have the distance. We compare, is the distance less than... Actually, let's not make the optimized way this night, like tonight, because it's like very late already. So I think I'm going to be fine with just, a semi-optimized one, let's say. Just with my, how do you call it? Yeah, you know what I mean. The thing I explained just before. Actually, disjoint union set. So we have the distance. If the distance is less than the minimum distance, then I do minimum distance equals distance, easy, and min over, wait, actually, yeah, anyways, so min over point id, well, index, over point index, let's say, well, connected point index, 0. I mean, let's say it's I, actually, so that we can detect when there's a problem. I guess, I mean, I guess yeah, let's just, if I equals j, then let's continue. And we can actually optimize it even better. Because, yeah, okay, this is actually a pretty good point. Instead of doing O(n squared, you don't have to compare I with itself. You don't have to compare you don't have to compare 0 with 1 and 1 with 0, right? So you can actually just start j at I plus 1. This is it. And now you compare everything only one time. Or, yeah, you compare just every point one time and that's it. Okay, this is actually not going to be naive, I suppose. So if we do this, that means I is never going to be j. So we can just remove this. So then we have the distance. We get this. We have the connected point index. That is going to be j. And yeah, j. Let me check. Yeah. And then now that we have that, we have, yeah, okay, at the end, we are basically going to say that for this, we have the point to group, right? So we are going to say that j, actually connected point index, its value is going to become, actually, let me think. Maybe the opposite would be better for optimization purposes. Like basically I is going to become this. So the group of I is going to become the group, well, is going to point towards the group of the connected point. Actually, I actually don't know what is better. Maybe it's just the same. But anyway, we have that, okay? So we have different groups this way. And this is actually pretty awesome. Because in the end, instead of sorting and doing something in O log n, n log n, then we are going to just have the inverse Ackermann function to compute that, to retrieve the groups. But I guess we still need to loop over everything. So it's a ON instead of amortized ON instead of ON log n. So we save a log n on this. Yeah. So for this one, for I in range and B points, let's watch. I guess I actually want the amount of points per group. So only the 3 biggest, right? So can I optimize it somehow? What about 1, 2, 3? I can have some. Oh, there's actually some data structures that exist for that with a list that has a limited amount of elements and that is always sorted. So that's like a priority queue, but that is limited. Yeah, I think it's a priority queue that is limited in size. Hey, thanks for the raid! Black Silver, welcome, how are you? How are you doing? Did you do the Advent of Code too? Yeah, priority queue Python. Heap queue. Yeah, basically I don't need any of that. I can like do it myself because this is only for the 3 biggest things, right? So priority queue. I'm afraid of the second part actually. Just finished day 8. Oh, horrible. Easy. Trying to learn TDD, so not enough tests. Oh, TDD? Technical design documents? And yeah, we priority queue. Do you have that? Queue happened. Oh, it's an implementation. I mean, okay. I mean, I don't need this. Did the writing on part 1 also mess you up? So let's have a priority queue, let's say. This is going to be elements. Let's call it limited priority queue. Anyway, let's do that. Elements. So this is a list of ints. Wait. Custom priority queue. Elements. So this is supposed to be an ID, okay? This is supposed to be the parent ID, but then you have a number for everything. So this is actually like some kind of So yeah, let's say this is an element, but I guess okay, I guess I can actually do that. But inside it's not a list. is going to be a pair with an ID and basically a tuple of this. But I mean, it's a priority queue, so we can just, yeah, I mean, let's just keep it this way. So we have our queue. And the difference between the sorting and our priority queue is that we are only going to keep the top elements. Yeah, well, I think instead of nothing happens, I would have said the connections don't change. Yeah. I mean, okay, yeah, for me it was, I was thinking like that, because they are already part of the same group, right? And yeah, how is it actually called? Because I know it has a name, but I don't remember the priority queue with fixed size name. Bounded. Oh, bounded. Yeah, bounded is a great name. NB max elements is going to be 3 in our case. So this way I still have some flexibility for the second part. So I have the priority queue. For every point, I'm going to call get group, which doesn't exist, but trust me. For, let's say I, okay? Then I emplace, actually, find emplace. What should I do? Elements. I guess I want to push the group. I guess in my case it's like a custom. I don't really want to do that. I guess it's a custom. Because I actually want. I don't know. Because I want a custom comparator, and yeah, this is going to be complicated. So let's just do this. Lists. Wait, is it how you do in Python? And this is basically a group ID. Oh wait, you can't do that in Python. I think you can. Yeah, let's not do this. Group ID slash amount. Well, counted. Well, counting bounded counting priority queue. Okay, is it good this way? Okay, this should be good. So now I have a function that is going to be push that has a group that is an int. Now I'm going to basically check the. I mean, ideally I would do a binary search, but this is like for 3 elements, right? So I'm just going to compare probably with the last elements. So we have elements. Oh yeah, I guess I need the self. This self. Self dots elements. Yes. As index equals nb actually elements length. So we get the last index, and while this is not -1, because binary search would be faster, but not with small arrays, basically. So that's why we only have 3 elements. So last index. So we have the ID and we have the amount. Wait, that's not how it is. Let's actually have 3 of those. And this is basically squared distance. I guess it's a float. Yeah, maybe I should like make a class for that. But anyways. So I guess we have group. And we have square dist, which is a float. So if the square dist, wait, the square dist? Do I need the square dist? No, I don't need the square dist. Wait, do I? No, I don't. The text on day 8 was pretty bad. Yeah, lots of people saying that. Yeah, I actually don't need the distance because I'm just checking the groups, right? Yeah. So this is the biggest group, right? That I need. Wait, do I need the biggest group? Plan shortcut connections, 11 circuits. Multiply the sizes of the 3 largest circuits. Yeah, okay. So yeah, there's actually no sorting in that. There's actually no... Oh yeah, because it's the number, right? It's the amount that matters. Yeah, it's the amount. Never mind. That's the amount that matters. I got a bit confused with myself. Wait, but if it's the amount, then... Yeah. Sorting 12 megabytes of connections takes less than 50 microseconds. It's actually compiled. So, you already have everything in your file, so everything is actually compiled and like run in compile time. Like that's actually possible. Like in C++, you have const and that stuff, right? Like the compiler can actually optimize the way. So maybe that's actually why there was so good performance in the previous programs. Compiling in the input.exe is cheating. Oh yeah, right. Yeah, you're right. Yes, it's reading input, so I guess yeah, you're right. So runtime becomes the compile time. So yeah, what? So I guess what I'm doing is just stupid. Why am I doing that? What I want is count. I want to count. Oh wait, this is actually... Yeah, never mind. This actually makes sense. I actually need that. So the group and the amount. Okay. So if guess I do need to know the amount, right? So here we go. If this one is less or equal, if it's less, let's say, than the amount, then I guess we continue. Something like this. Then I minus minus. Well, last index minus minus. I guess this is not the last index anymore. Okay, I. Let's do that. Now if I well, let's just do I plus equal 1 at the end, so that it is not like -1 or this kind of stuff, right? So that it actually becomes the index we want to replace it. Okay, so if I is bigger than NV max NV max elements equal to, then we return. If not, sorry, then we are going to push. Well, push. I guess we are going to do elements, self.elements. As the current I equals the group ID, so group, and the new amount. The difference is that if we do that, it's not going to be sorted anymore. Well, it's going to be, it's actually going to stay sorted, but we want to keep the free first, so we have to push back the element we are going to replace. So it's actually an insertion. And that means that for j in range, with this being basically last index equal this, right? Actually, yeah. While this is not I, we are going to have the same thing actually, just that equals that with I minus 1, I minus 1, j minus 1, I suppose, equals j. Wait, is it? Actually, it's the opposite. J equals j minus 1, and we know since it's stopping, let's just do it the opposite way, right? Since it's stopping at I, and I is a correct index, that means j minus 1 is always going to be valid, because this is going to be I at one point. So that's like actually insertion. Okay, that should be good. So now that we have our bounded counting priority queuing, now that we have that, we have this, we can push, and now we have to get the group, right? It's really fast in Bun 2 because Bun is just zig with extra steps. Oh. So let's get our group. And this is the interesting part about disjoint union set. Let's actually just comment it. Let's remove this. On setup disjoint union set. And the get group, what is it going to be? I guess we can make a function, an actual one this time. Actually, can I just put it inside? Oh, I can. Yeah, I can. Great. I'm just going to do that because I don't want to pass additional parameters here. Because basically, you know, it's like it's like um, a data structure, a disjoint union set. So I kind of want to I don't want to create the class basically. So get group. Actually, I guess this is it. Yeah, we have it together now. So get group we have for I. This is an element. Ah, yeah, I. And yeah, we are going to basically, while this is the part where it's like really good, like you know how we initialized each point to a group of its own index, right? That means that there is a point, uh, like if I actually put it in, like if I get the group of this, that means there is, you know, there are points that are equals to themselves, kind of, right? And while this is not equal, I'm going to do, um, this is going to be crazy. I'm going to do this. Do you understand why? This is, I love this. And this is like inverse Ackermann complexity. And I hope it's written like that. It's spelled like that. But anyways, and yeah, and basically we are going to update the current group of I to its parent group. So join union set. Let me show you something. So basically, you know how we made a graph like that, right? Where basically you have a node that is going to point to itself, and you have children that point to themselves at first, but then that points to other nodes that, you know, they have intersected with, right? And the thing is, what we are doing is if 9 is not pointing towards itself, and is pointing towards, for example, 7, then the new group of 9, what is 9 going to point to? It's going to point to the parent of that, the parent of its parent. So now 9 is going to point to 6 directly. And it's actually, you know, going to optimize future sampling too, which is like pretty great. And yeah, and what if 7 is trying to update to the parent of 6, because 6 doesn't have a parent, right? But actually it does, because as we set it at the beginning, 6 is pointing to itself. So it's actually not a problem. So now, so wait, actually, is that actually the stopping condition? Because 9 is going to point to 6. So this is actually not the correct stopping condition. Let me think. I guess the correct one is actually this. Yeah. So if the parent and the parent of the parent are different, then that means the parent is not the group, right? So then we can continue. Is 7 is the parent, and the parent of the parent the same? Yes, it's 6. So that means just keeping the parent is fine. Okay, that's good. Should be like that. And at the end, now that we have updated, we can just return the group, which is this, right? Here we go. So we have the group, and maybe that's just it actually. And now that well, actually at the end we have the three different elements in our priority queue, right? So what that means is probably that we can get those three elements of the three largest circuits, get those three elements and multiply them, and that's it. So I'm just going to watch. Actually, wait, I actually forgot something. So I have a push, right? And I have the group. But what if the group is the same? So what if, okay. So yeah, now what if, self elements, what if the group of that is equal to the group of this? Actually, is it amount? Wait. The amount is going to be different because we don't actually currently have the amount, right? So this is actually a problem. I guess since it's only three elements, we can check everything, right? Like we could basically check every element to check if it's the same group ID. That's kind of a bit bad, right? But I mean, if it's three elements, it's fine. Uh, is it? I can optimize that. I don't have to store the elements there. I don't have to store the elements there. I can just have a pointer. So this is, wait, int amount. Elements. Yeah, that's what I wanted to do. I wanted a list that was counting like a hash map. So I have the group ID, right? And I guess I need a function to get the amount. How can I get that? I could have a callback, but it's like not really optimized, right? So I mean, I guess I can have like a context, like NB elements per group. I don't like putting it in the bounded counting priority. I can, okay, but that's fine. say list of integers. Yeah. And we are just going to, so elements is just an int. Or rather, I guess elements. Well, let's have sorted elements. Here we go. Then we have the amount nb. Wait. Element. Element to size. We can call it like that. But this, yeah, okay, this is fine. I'm going to set it outside. So wait, what if it is equal? Element to size. So yeah, basically on top of that, I just need point to group, and I have group size, which is going to be the same. That starts at 0. I guess at 1 actually. Okay. And now towards the end. Actually, let me put 0. And at the end we count, right? So we are just going to have group size group. Well, group to size group, and we are going to do plus equal 1, and then we are going to push it back into the queue, and the queue is going to update that. And yeah, let's just make sure that our queue has a correct reference for elements to size, which is group to size. So we push. And yeah, the only problem, if it's the same, then that means it's stopping somewhere. Wait, minus, yeah, here. So if actually, what if it's equal? What if it's equal? I mean, let's just add something like if group equals, I guess this is the amount I want. So this is self dot elements to size. And I need the group. And if the groups are equal, then I just return. Okay, then I minus minus. This is a bit ugly, but I mean, there are only three things, so that's fine. And yeah, I mean, that should be fine. That should be fine. I feel like there's a lot of problems, but what's that? Is that this? Time? Yeah, okay. Okay, you know what? Let's try. Okay. There's going to be a problem. Yep. For split. Oh no. Okay. So this is chords. And oh yeah, I int. Yeah, this is flats. These are flats. So chords 0. Oh wait, actually it's split with commas. Wait, so actually maybe this was fine. It's just that I have to put a comma. And this is, yep, flat. Yeah, I'm missing one positional argument amount. Do I? Actually, I don't. I mean, I guess it will be better, but I can just do this amount. Yeah, let's just do that for like, it's like the same comparison which it's like not very optimized, but yeah. Okay, bonding amount. Okay, yeah, indeed, you're right. Let's remove it. Okay, so insertion. What's the deal? 0. What if... Yeah, so when there is 0 element, I guess that makes sense. Um, I guess in that case we can just what? Max elements? Can I just init? And we have elements to size is something that I'm not going to decide. And sorted elements though is going to be is going to be I was going to put -1, but actually I won't. Yeah, because I mean I guess we're starting from the last index anyways, right? So if I is bigger than I guess last index is literally -1. Wait, actually initialize that -1. Okay, so yeah, if it's so it's going to be 0 first. So if I mean if this is less ah if so we have the last index. This is 0 at first, and I is going to be 0. So if this is equal to the last index, what happens? guess we're just going to set. But yeah, in this case, I guess it's just if I is more or equal. Yeah, what is this is 0. This is so yeah, this is -1. Oh wait, no, this is -1. This is good. And it stays -1. So if this is higher than -1, then we just push. Right. So I guess we can go there. Yeah. That's it. Poof. That happened. This. And here we go. I guess ideally we want like a fixed array, but I feel like that's a bit complicated to compare with like dummy things. So no attributes. Really? Really? So wait, is that not Python? Because I do feel like Python class function, member class, member function, I suppose. So this is self. Wow, this is so hard to see. Wait. Why is it so pixelated? Okay. Please, AI, help me. Self. So yeah, you do use self. You do use self. So what's the deal? Self.age. Self. Not self. So self dot sorted elements, self dot elements to size. Oh, is it because it's empty? Wait, but oh right. Okay, that's fine. That's fine. This one is set outside, so that's fine. Oh, it already. Yeah, of course it was 0. So yeah, now what's the problem? The problem is that it's returning literally 0. So maybe that's a problem. So instead, let's just get sorted elements 0 times 1 times this. But these are groups, right? So what we are going to do is use this to get the size of everything. Let's just go back maybe. Something like that. It's a bit cleaner. We can zoom in. And yeah, let's try. This is a lot. This is probably wrong. So this is supposed to be 40. 40 for what? So this is actually input. What I want is test input. And this is 8,000, which is a bit more than 40, I believe. So now let's see what the problem is. Let's debug. So we have 11 circuits. One circuit which contains 5 junction boxes. So yeah, let's actually just check group to size, because that should show us like a lot actually. Okay, the last one has 20 elements. Oh. Wait. So everything is linked together. Oh, that's crazy. Minimum distance. Because they're not checking with each other. Oh. Okay, I get it. I get it. I understand. I understand. I think there might be some loop too. That might be a problem here. But well, I guess maybe the real condition is like I is not equal to this. Never mind. Maybe it's both. Never mind. Okay, yeah, never mind. I think that's fine. But yeah, for this one, it's just not checking. I mean, that's kind of good what I'm doing, but I'm not considering that I have to stop at one point. I have to not go past a certain distance for certain points. So I mean, for example, if I start at 0, let's do that, and I plus I equals j leads to a continue, then if I do that, that should work. That should work. But it's just going to be bad. Or maybe it's going to loop forever, but oh no. It's not even here. Wait, is it really looping forever? Wait, where is it? Wait, where is it? It's not there? It's not there? Oh, it's there. Oh, it's the get group. Oh, okay. Interesting. So what's the deal? So we have this equal, I think there's just a loop between the two of those. Then we have this. And I is 4. Oh, it's 1. Wait, what? So we have 1. Oh, no. 1 that is going to 6. So 1, 2, 3, 4, 5, 6. That is going to... Wait, so what's the problem? Wait, it's actually not updating? Or maybe it's just because I'm not doing the... Wait, no, this is actually not updating. Why? Six, 4. Wait, this is pretty crazy. And the current one... I mean, basically I'm supposed to... Ah. It's the same array, right? I mean, I'm kind of... Yeah, never mind. So 6, 4. What if I loop one time? 4. Okay, so there is a loop. Yeah, okay, there is a loop. So yeah, I guess I have to check if I mean, what is I? It's 1, right? Yeah. So I guess it's I mean, this is because of this, right? So I don't really like it, but yeah. If there is that, and let's say this is not equal to this, that should fix it, at least, I believe. Actually, maybe it's because just I made the tree wrong. I think I just made the tree wrong. Maybe it's when I insert that I have to fuse. No, I don't think I do. Yeah, there's definitely a problem. There's definitely a problem in the creation of the tree. I have to check if it's not intersecting, then I connect. So let's get the group. Maybe it's when I set it. Oh yeah, that's it. That's what I had wrong. I have to get the group. I have to get the group. Okay, now it should be better. Please. Hey! Okay, it is better. But now it's 125. And it should be 40. So this is a lot better, right? At least. Breakpoint. Debug. Group to size. 3, 4, 4, 3, 3, 3, 2, 5. 4, 3, 3. Wait, so what did I get? 4, 3, 3. 4 times 3, 12. Times 3, 36. What the hell? So this is supposed to be 5, 4, 2. Wait. Yeah. 5, 4, 2. 40. And I have... Wait, this is actually supposed to be 0, right? Oh, no, never mind. So this one is actually... What is it? 19. Oh, wait. Is the cure actually working? Yeah, so this is working. What is this? 19. Never mind, this is not working. Oh, yeah, this is not working. What about this? 19. Wait, the two are 19. Wait, all of those are 19. So that's 5 times 5 times 5. 25. $125. So yeah, it's actually my priority queue that is not working right now. What is this? If group equals sorted element. I mean, yeah. That should be it. So sorted elements I. Maybe it's when I do this. Oh. Oh. From last index to I. No, that's fine. So yeah, let's just check what happens with this. So the first time I do the things, I add... Oh. Yeah, let's return. That makes a lot more sense now. What now? I guess I can debug console. Okay, so this is still the same. And the reason is because sorted elements are just the same values. So let's redo. Let's try again. With this. So I happened. Okay, good. With the next group is 6. What is sorted elements? 19, okay. Append. Yep, this is good. Group is 13. What is self sorted elements? So this is actually not sorted, as you can see. So yeah, let's restart. Boom, boom. So 13. Oh, actually it's the size, right? So actually it might be sorted. Oh wait, this one is 19. So I have all of those. Okay. I mean, yeah, it's not supposed to. If it's less, then it's supposed to. I mean, if it's. Oh, wait. It's supposed to continue as long as this one is less. So if this is equal, then it's stopping, basically. Yeah, it makes sense. So that doesn't work. So if this is equal, it is stopping. And in that case, we want to check here. If this is the same, then we return. Here we go. Okay. What if this is higher? Okay. What if this is equal to -1? $100. Okay, that changed, I suppose. But yeah, if it's equal, then it's still going to not be good. I guess here? Let's try. I feel like I'm just trying everything in. Anything in it. Yeah. Out of range. So, yeah, I mean, yeah. Yeah, okay, I understand. Let's just put it here. Let's test if this is less than less or equal to the last index, and this equals this, then we return. Wait, really? It's supposed to be -1. Oh. Yeah, I'm. Wait, I is -1 too. Oh, so I guess it is equal. Okay, this is actually a pretty funny. I don't know what to say. That's pretty funny, let's say. Okay, so if I get the amount, and if this is less, but I guess I is going to be -1 at this rate. So I guess the real thing is we check if this is not -1. So many conditions. Oh no, this is going to be so bad. Okay. Let's try again. I mean, I kind of know what it is, but yeah. 19, 6, 13, 19. Here we go. 1, 1, So now this is 0. Okay, and the first element is of self is 19. So is I equal to -1? Nope. And is it less than the last index? Yes. And is the group equal to this? It is. So in that case, we return. I mean, looks good actually now. Let's actually complete. 4, 3, 3, 3, 2, 5. Oh, wait. 4, wait, 5, 4. We circuits which contain 2 junction boxes, and 7 with 1. So I guess one of the problem is the one that has 4, 3, 2, 5. Group to size 5, 4. And yeah, basically the ones that are free, that have three things. I guess it was supposed to be 2, right? Oh. 4 junction boxes. So 1, 5, 1, 4, 2, 2. And yeah, I'm missing the ones that are just 1. Wait. Wait, 7 circuits which each contain a single. Wait, what? How can it contain only a single junction box? 7. Wait, what? 7? I'm not understanding the problem, I think. Because if you have to make pairs, then how can you have single junction boxes? Put that together, or this one and this one. Oh, can you connect only one? No! There is a single circuit which contains 2 junction boxes. That's what everyone said. That's when everyone said. The remaining 18 junction boxes remain in their own individual circuits. Okay, this one and this one. So connecting them. There is now a single circuit which contains 3. Okay. This one and this one. There is a circuit. No. Because these 2 junction boxes were already in the same circuit, nothing happens. Yeah, they're already in the same circuit, right? So that's fine. Well, actually, that's what I thought. It's actually supposed to be fine. So, okay. Okay. Collisions. Priority queue. Dot sorted elements. Oh, we have 219 again. We have 219 again. Wait. How is it? How is it? Wait, really? How is it? How is it possible? You know what? Let's just have something stupid. Oh, I mean, okay, I guess it makes sense. Let's have I equals, let's have k equals 0. Well, for k in range and b. Mm, just length, I suppose. If sorted elements self.sorted elements k equals group, then I return. So that way I'm sure that there is no conflict, okay? This is O1, this is, well, ON, I mean, this is kind of bad, but this is fine. And this is 60. Okay, this is already pretty different, which is kind of good. Let's check how it is. So this is supposed to be 40, right? 5 times 4 times 2. Yeah. 5 times 4 times... And we have freeze, which is not good. I have a lot of bugs. At least this looks like it's fine. Let's check. What was it? Group to size 0, 1, 2. Yeah, okay, the priority queue is correct. So now the problem is really with my functions actually, which is kind of bad. Can I just do this instead? Like what I did at the beginning? Uh-oh. Wait, what? How? Wait, how is it possible? $19. Wait, how? A plus 1? Oh, wait, what? Actually, no. Actually, I don't know. Wait, how is it? Huh. Okay. Square distance. Have the minimum. Why it gets grouped though? Oh yeah, never mind. Yeah, that's fine. Uh, yeah, this is fine. This is fine. Maybe I... Anyway, so yeah, there was a problem with something somewhere. I actually don't even remember where it was. Was it the priority queue? Yeah, I think it was the sorted element of the priority queue. So this is 0. Never mind. This is 19. And we continue. We append, we return. Fine. We push. For every element in this. Okay. Wait, that was equal? 19. Wait, I guess it was equal. Hello chat, hello, Dusky, yeah, Dusky Elf Dev. Welcome, how are you? Yeah, let's actually map. Did you do the Advent of Code? Do you know what it is? Point to group. Point to group is actually going to be like very important. $19.5. I guess we actually want to check it after the get group. So now it should be updated. And basically we have everything pointing to 19. What the Right, this is the problem. What? Wait, what? Wait, this is really scary. Actually. I've also been doing AOC 2025 or in Zig this year. Oh, yeah, someone else have been using Zig. Like they've been talking about Zig in the chats a bit, but I've never used it myself. Yeah, looks like some kind of JavaScript kind of thing. With like the FN, with like basically some types that are just, not put in the functions. Yeah, this kind of stuff. Zig is a systems programming language, more like C but with modern syntax. Oh, I hate modern syntax. Why do people want that modern syntax? I see, I see. But yeah, it looks nice actually. Like you have the imports. I guess you do have you know, the thing is at the end. Try. Oh, you do have yeah, ranges. I see. I think. Maybe not. No, never mind. Never mind. This is not a range. No, though it's actually nice. It's 0.15.2. We'll probably get 1.0 in a few years. It's been like a decade. Okay. It's just to continue saying, yeah, it's a new language. It's fine if there's something not great. Just kidding. But yeah, it actually looked nice. I wish so much that there was a language like C++, but like with nice stuff. Like I don't understand why they're not putting the types at the beginning. Like C Sharp, like Java, like C++, like C. Like, I guess you actually have that. Uh, well, actually not there, right? You have the two the two thingies. I feel like that's just adding extra characters. I don't like it. But I mean, it does look nice, though, overall. Singly links list, hash map. Yeah, I mean that's not C++. That's great. Like in C++, you have map. You don't know if it's a hash map or, well, actually, I know it's a tree, right? And then you have unordered map. Like, okay. Why not sorted map? You see 2024 I did in Rust. Oh. It's fine. Things can still change in the language. Yeah, yeah. I mean, I'm not trash talking, right? I mean, I think it looks nice. It looks fine. The import looks alrightish. I do like the C++ kind of thing like that. You know, the using namespace kind of thing. I guess it uses std too, like in Rust too. Get pointer. Yeah, you have pointers, allocators. And yeah, why is everyone pointing to 19? That's crazy. Group to size. Uh, oh no, never mind. I know why. Uh, what if I put min dist? Yeah. I. Uh, maybe I should. Maybe I should switch. Should I? Yeah, yeah, that's probably better this way. I don't know if it's going to solve anything, but at least let's check. Group to size. Wait, it actually looks 5. There is no 4. But I mean, okay. I mean, I know this is. I mean, yeah, it's normal that it's not supposed to work anyways. Um, makes sense. Does it? Wait, no, it's actually. Uh, oh yeah, the min dist. That's why. It's just modules, and modules are just compile time structs. Yeah, yeah, I know. That's the coolest feature about Zig. It's compile time everything possible, similar to TypeScript, but more procedural. Yeah, just like Rust, right? You have compile time everything too. I guess that's kind of the points I don't like about C++. It's, you know, the sFinae template, uh, and like all the weird things, right? Like the weird syntax for sFinae. So yeah, he actually wants the minimum min, well, closest square list plot. Let's have this. And let's have something like, instead of min dist, I guess we can check. Uh, for, wait, are we doing that for J? I guess we can do this for J. I guess we're doing that for I. If so, then we are going to update I. Um, I equal this. It's the square distance, but you know. And I mean, for J, I guess we are going to update too, right? Connected point index. Wait. Why is it here? Get group. Wait, why is it here? Isn't it supposed to be... Wait, yeah, it's supposed to be here. Yeah, that's why it was 19 everywhere. Wait, when did I move this? Oh, I mean, yeah, of course it wasn't going to work. Of course it wasn't going to work. Oh, no. Anyway, j equals the minimum between this and this. Okay. Do, 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 do. Seven? What? Oh no. But yeah, sorry if I'm like a bit proof right, it's like 4 a.m. I really just want to finish this one using my thing. Well, almost 5 a.m. Oh, tomorrow is going to be bad. It's going to be bad. I should have stuffed. I should have stuffed so much. Closest distance, I. Oh, wait. Oh, never mind. Wait, should I do that? Yeah, actually, it might have been fine the way it was before. Yeah, for each point, we get the closest. And then we set. Yeah, what if it's... Can I just make them point to each other? Wait. So, yeah, okay, let's do that. And then we have I that is going to point to its closest. So this is the closest. And what? Maybe I just have to set it here instead of there. Mean distance. I mean, I might not need that. So I'm setting the closest distance. I'm going to set it here too. Yeah. Yeah. And if it's changing actually, then what? I mean, I guess that's it then. Hey, your code looks almost the same as mine, but I didn't see the priority queue. Oh. Yeah, I'm trying to do the disjoint union set. Two, three, two. Wait, no, there's a 3. 20? No, never mind. 6? What the hell? Yeah, I feel like I'm just destroying my code at this point. It's just getting worse and worse. Maybe I should just focus on having something simple first. Connect point index. But yeah, yeah. Basically, well, I don't know if you know the data structure. Maybe you just came into yourself just by thinking stuff. But basically, the goal is to you have a list of groups for each element, and you have each element pointing to itself, to its own group, and then you update it, and then basically when you get the group, you have you call the inverse Ackermann. Not at all. Well, you have a function that has inverse Ackermann complexity, so that's very fast, almost like it's amortized O1. But yeah, I just don't know why it's not working. Um, closest. I mean, I guess I could update both. So it's like, um, yeah, I think, okay, I think that's why there's a problem. If list is less than closest list of j, then I'm going to update this one with the distance. But I'm also going to update the group of this with itself, maybe? In Zig, I just had a simple field on each junction, having its group ID, which is ON worst case optimization, and I still get the answer in less than a second. Junction. Oh. Simple field on each junction. As in like some kind of hash map, or wait, which is ON worst case? I mean, you obviously can't fix it in ON time, right? But I guess you're talking about. Huh. Like for what part? For so wait, this equal. I mean, yeah, I guess I can just put itself. Yeah, wait, I have some elements should be 1, right? One of the circuits of size 2 produces 40. So I think I'm not understanding something. And 7 circuits, which each contain a single junction box. So yeah, I'm not understanding that. How can you have a single junction box? I think I didn't understand something correctly. When to find the group ID. Oh, yeah, that's. Wait, the overall solution was something like. Oh, oof, oof. Okay, that's a lot. Oof. Yeah. 10 shortest connections. Okay. There are 11 circuits, and circuits each contain 5. 7 circuits contain a single junction. I don't understand that. How can it be a single one? Like really, I really don't understand that. How can it be a single one if you have to connect to the closest one? Oh wait. Oh wait, this is not the end, right? No, never mind. Wait. Because you only find the 10 minimum pairs. Wait, is it 10 minimum pairs? Oh, yeah. It's not in bold. Oh. Oh wait. I understand what they meant now. I understand what they meant. You're saving me. You don't know at what point you're saving me. Thank you a lot. Thank you so much. 1000 shortest for the big problems that yeah. I guess I understood that there were already 1000 inside and that you just had to to check them, right? But no, that's not it. No. Okay, so yeah, that's a completely different problem. Yeah, thank you a lot. I guess I'll just be going to sleep then. It's like, yeah, work is going to be hard for tomorrow, but thank you a lot. You saved me. Yeah, I'll probably be going. Well, I mean, tomorrow I might be a bit tired, honestly, but if not, I'll try streaming it. Uh, Actually, yeah, it depends, but if not tomorrow, I'll be streaming the day after that, so feel free to come back again. Uh, Maybe a bit earlier, because I don't know if you know, I'll continue staying awake so long. But what about Advent of God? Oh, we have some C sharp.
Comment at some of the right lines here, and I can run a bench to see.
Boop. Here we go. We have this guy coding in C sharp. Looks great. My solution. I don't know. A lot of people sent me their solutions, but I don't know if I want to get spoiled, right? It's in Zig? Okay, I'm just going to check the Zig, okay? Distance squared. So, oh, that's actually great. Well done. Like, some people don't, you know, just use the square roots. And while so many things. I mean, I'm not saying that's bad because I'm not really looking at the meaning because I don't want to get spoiled. But yeah, we do have some very similar code.
Part 1 and part 2 right lines on it.
Yeah.
Let me just keep it there.
And yeah, let me maybe just fix it in the ID. Oh, it's ad break. No. Well, I mean, um, sorry about that. So yeah, let me just start the raid to NKCSS. Oh, welcome back. And yeah, I was saying, I'm not really looking at the meaning because I don't want to get spoiled, but basically, I guess if you're only taking the 1000 closest distances, then that means you want a priority queue or like some kind of stuff that is sorting depending on the distance anyways. And I guess you actually want to convert your things into connections. So you have maybe a class connections and that class connection has like the two IDs, right? And that connection has a distance, and you sort the connection depending on the distance, so with a priority queue. And oh, actually, no, because you can only bind one element one time, right? I mean, I guess that's fine. Yeah, I guess I'll have to see another time, maybe. Are you talking about KD trees? I'm not talking about a KD tree. I'm not talking about a KD tree. I'm talking about no, I'm not talking about a special about spatial partitioning. I mean, you can do some spatial partitioning, right? You can have a KD tree, you can have an oak tree, you can have a grid, you can have I guess you could have sweeping, you can have what do you have? You can have stuff, right? Any other trees. But no. Uh, no. I mean, I guess you could use. I think grids are like pretty fast too. Uh, for this kind of problem, because I guess trees are nice if you have. Actually, let me think. Oh, wait, did we actually raid? Wait, I actually didn't raid. Wait, why? What happened? Wait. Oh, raid. I did raid. Well, in that case,